out the audio because I can listen myself on Zoom. Yeah. What is this? Okay. Should I say something? Click on something. Got it. Okay, that's fine. 20 seconds. So I just say something for 20 seconds. So, okay, so I typically give this tutorial in a kind of Blackboard format, but so since we're just having like 3, decided in the end to make something which is more of a taster of this research field. So I apologize for the theoretical physicists who are eager to see computations. This is going to be just trying to motivate some of the ideas. And then if you're really interested in diving more, there's going to be a chance for that. Like, for instance, I have some lecture notes where I have put here together just as some references in case you really want to see the computations in detail. So instead of going into detail, I'm just going to be motivating some high-level ideas. And if you want to know more, please come chat with me. And I can point you towards different kind of resources that you can find where computations are detailed. So I'm just saying that because, you know, I'm the kind of physicist that really like to see the computations and really like to doing the maths. And so I usually prefer things on the blackboard, but okay, let's follow this plan. Okay, so most of what I'm going to be telling about you today, it's detailed in these 4 lectures that I gave in Princeton 2 years ago. And some of the last part is on this lecture notes on a lecture that I gave in Cargès last year. Okay, so let's start. What is the plan for the tutorial? So we're going to start today quite slow, trying to review some key ideas on statistical physics that I assume most of you know already, but bear with me. I'm going to be trying to give you a computational point of view on these ideas, even though these are like classical things in statistical physics. I'm going to try to build up some of the language that we're going to be using towards the learning part of the course. And then for tomorrow and after tomorrow, you're going to be seeing some of the more kind of machine learning content. So the plan for today is to give you a historical introduction as well as motivating the connection between statistical physics and learning theory. So more precisely, what is the plan? So first, I will try to convince you why statistical physics and machine learning were made for each other. Then I'm going to tell you a little bit of a brief history of this happy marriage. And finally, I'm going to be looking concretely at one example where is one of the classical kind of applications. It's not exactly machine learning. I would say it's more theoretical computer science, where ideas of statistical physics have been used to define some notion of computational complexity in the context of learning, inference problems, constraint satisfaction problems. So there's a whole class of problems where most of the activity for the past, let's say, 10 years have been in, and more recently we started like shifting towards learning theory, although the tools are very similar. Okay, so let's get started. Let's get started with the very basics, which is just like motivating statistical physics, right? So this is something we all see in Statistical Physics 101. What is the key idea of statistical physics is that when we look at many-body systems, it very quickly becomes untractable to just study the laws of mechanics, right? So if you start to think about writing all the equations of motion for all particles in a very large system, let's say the classical example of a gas in a box, very quickly become untractable to do this, even computation. You just need the amount of computation in the universe to be able to even simulate the system, right? So the idea of statistical physics is just to say, okay, instead of taking a perspective that we're going to try to track exactly what is going on at the microscopic level, we're going to take back and say, in the end of the day, we are only interested in macroscopic properties of the system. We are not interested to know what particle 1 is doing, what is the full trajectory of particle 1. We are interested in some kind of aggregate properties of the particles, such as like concepts like the temperature of the system. So the idea of statistical physics is exactly to treat the system statistically. And so here, the key idea is going to be to define aggregates, which in the context of statistics, just pure statistics, is what statisticians call statistics. Statistics are macroscopic aggregates of quantities that we want to study. So yeah, this is analytically and computationally intractable. So the key idea is to introduce a probabilistic approach, and this is done through introducing a distribution over the configurations of the system. So here, configuration, I'm going to be using this language to refer to any kind of a ensemble of degrees of freedom that we want to study. And so the key probabilistic idea is that, okay, let's introduce a measure on the system that weights differently configurations according to the energy. So that's the Boltzmann-Gibbs construction. And then the goal of the problem becomes to study limits of this probability distribution. Now, let me make some remarks about that. Is that first, when this temperature parameter goes to infinity, so when this inverse temperature parameter goes to infinity, so the temperature goes to 0, this probability measure is going to peak around configurations that minimize the energy. So this is what we call ground state in physics. But here you already can see like one first connection with learning theory and statistical physics is the fact that most of problems in learning theory that we are interested can be framed as the minimum of some function over some high dimensional variables, okay? So any learning problem that can be written as the minimum of some functions of some collective variables can be framed in a probabilistic framework of statistical physics by defining this type of measure and then taking the temperature to 0 if you really want to study the minimum. The way it goes in statistical physics is that we motivate that in order to understand the properties of this high dimensional probability measure, we look at a quantity called the free energy or the free energy density. And this is just like the log partition function. So in statistics, this is what is called the evidence. And this is closely related to a quantity in information theory called the mutual information of the system. So it's also the moment generating function of the distribution. And, you know, as long as everything is well behaved, understanding the moment generating function is equivalent to understanding the statistics of the distribution. So the key idea that I'm going to be using in the following and kind of permeates all the applications of statistical physics to machine learning is this idea of order parameter or summary statistics. So what is that? So is exactly this, what I was motivating before, is that we are not necessarily interested into particular configurations of the system, but aggregates of this configuration. So we define some type of variable, which is a macroscopic variable that aggregates properties of the degrees of freedom. And typically, these summary statistics, they live in a lower dimensional space. So here I'm kind of abstractly defining that, but very soon we're going to loop this into a context where all of you are familiar with, and this is going to make maybe more sense. So once we define these macroscopic variables that we'd like to describe, the goal is to write the probability measure in terms of these variables. And what typically is going to happen is that in some asymptotic limit or thermodynamic limit, the system in the language of these variables is going to satisfy what we call a large deviation principle. So this is an idea that is very old. In physics, we usually refer to it as a Laplace or saddle point method, and has been formalized in maths as what we call a large deviation principle, which is the fact that the measure is going to be peaking into some configurations that extremize some potential function, and this potential function lives on the space of the summary statistics. And this is the key idea, because if we achieve at showing something like that, we can look at hindsight and we achieve at mapping a high dimensional probability problem into the study of a low dimensional, let's say, extremization or minimization problem. So this is like, let's say, major progress. If we manage to actually show that such relationship exists, essentially, we have simplified a lot the problem. Of course, it's not always that this is going to hold. Some properties of the system will need to hold in order for this type of relationship to be true. But all the applications that we're going to be discussing about will rely on this type of property, this large deviation principle, that tells you that actually the system in this space of summary statistics has a behavior which is controlled by this extremization problem. Okay, by the way, I didn't say, but it goes without saying that please feel free to interrupt me and have a discussion. I have a lot of material and I don't mind like not finishing it. So it's more important that we keep a conversation. So if any of this is foreign to you, so I'm going quite fast here in the beginning because I assume that some of this is familiar to most of you. But if it is not, please interrupt me, okay? Yes, so what I denote there by k is equals to theta n of 1, meaning that as n grows large in the thermodynamic limit, we assume that this space where this aggregate summary statistic lives is small, is like constant with respect to the growing dimension. And this is the key idea. So we are very much used to that in the context of statistical physics, but it took a long time for statisticians to get around this idea. And here I'm showing you a quote of a paper written by a very influential statistician called David Donohoe. So he's in Stanford. That wrote this. It's not exactly a paper. It's kind of more of an opinion paper where he talks about the curses and blessings of dimensionality. So the curse of dimensionality is the fact that when you are in high dimensions, doing learning is hard. And typically, many of the problems that we're going to be discussing later in the course, they are hard because these spaces that we are considering are very big. And studying probability in high dimension is a hard problem, like sampling, optimization, everything in high dimensions is hard. However, on the other hand, while high dimension is a curse, what Donohoe was pointing to is that sometimes it's also a blessing. And this is exactly due to the fact of this concentration phenomena that comes from large deviation. And so here I'm going to quote him: the blessings of dimensionality are less widely noted, but they include the concentration of measure phenomena, the so-called geometry of Banach spaces, which means that certain random fluctuations are very well controlled in high dimensions. And the success of asymptotic methods used widely in mathematical statistics and statistical physics, which suggests that statements about very high dimensional settings might be made where moderate dimensions would be too complicated. So this is like essentially restating what I just said. It's something that is very intuitive, I think, for physicists, but for statisticians, it took a while for them to realize that high dimensions can also be good. So the last thing I would like to discuss before looking at a concrete example is this picture of how to describe states of matter in terms of this summary statistics description. So one of the classic ways of describing phases in physics is by looking at the free entropy or free energy potential and identifying phases in terms of minima of this energy potential. And so here I'm showing just one random example for graphene. So for example, here you have like configurations of carbon atoms, you have different local minima that corresponds to different arrangements of carbons. And as you can see, so this plot is kind of a sketch of what this large deviation potential looks like for a material. And the important fact about this is that first, there are many minima that corresponds to different configurations that the system can be found in the thermodynamic limit. And what is very important is that since this plot is in the space of the summary statistics, even though the barriers might be small in this space, when you go back to the space of configurations, the space of the degrees of freedom, jumping these barriers in the limit costs you a lot, right? Because these barriers are actually extensive. They scale the dimension, and the dimension diverges, and therefore crossing them essentially costs infinite energy. Now, this is important because it means that these different states, even though if they are not like global minima, they are stable. And this is what we call metastability, is the fact that in the thermodynamic limit, even though the system might want to go to the ground state, the state of minimum energy, the fact that there is a competition between energy and entropy in the space of the summary statistics means that the system can get trapped into one of these local minima, depending on how you thermalize it. And each of these phases that correspond to each of these minima have very different physical properties, right? So diamond, which is a local minima, is very different from graphite. And actually, that's the whole point of why diamond is expensive, is that it is stable. It doesn't relax into graphite into a finite amount of time. So yeah, as I was saying, this is the way we like to think as physicists in terms of like phases of matter. And here is the statement that the time you would need to wait to jump to relax from one of these minimum to the other is proportional to the exponential of the energy barrier, and the energy barrier is extensive because exactly we are in this space where order 1 moves in this space, our order n moves into the configuration space. And so here I have one video to illustrate that. So I don't know here in Colombia how picky you are about your beer, but I come from Brazil, and Brazil is very hot. And in Brazil, the bars they display the temperature of the beer in front of the bar. So the way you choose a bar is that you go out with your friends, you go to the square. There are many bars, and you look which one has the coldest beer. Now the beer freezes at -4 degrees, and so the bars try to be as close as possible to this critical temperature without crossing it, because otherwise it's not beer anymore, right? And so when the waiter serves the beer, they are very careful opening the beer, because small thermal fluctuations around the transition point can make it to cross this barrier, because you're very close to the temperature of the phase transition. And if the beer freezes while the waiter is opening, he has to change the beer. So the waiters understand very well the concept of metastability in Brazil. So I don't know in Colombia, but here's an example. We can see exactly like how you can cross to another phase if you're very close to the critical temperature. Okay, so this has been quite abstract for now, and what I want to do in the next, like say 30 minutes is to review all these concepts in a model which we can essentially do all the maths in 30 minutes, and we can try to make all these things very concrete, which is the Curry-Weiss model. And again, here I'm going to go a bit fast because I assume most of you have seen this if you have studied statistical physics. But again, stop me if this is not the case. So the Curry-Weiss model is a simple statistical physics model of spins. So what I'm going to be thinking, like, spins are binary variables. So they are variables that live in the hypercube. So a configuration of spins is a vector of ±1, and you have n entries in these vectors. The energy function, which is the second ingredient that I need to define the problem, or the Hamiltonian, is given by an interaction term. And this interaction is essentially saying that spins want to align. And then a field term, an external field that says that the spins wants to align with the field. So in order to minimize the energy, you want to align the spins, but also compete to align with the field. So this model is, you might recognize it like, a simplification of the Ising model. So the Ising model is this model, but defined on a lattice. And here, essentially, we are taking the mean field or fully connected version of the Ising model because it makes it simpler to do calculations. For the purpose of, like, let's say, computer science, you can just think about, I give you a function on the hypercube and I want to minimize it. I want to find what is the minimum of this function on the hypercube. You don't need to care that this corresponds to some physics. So first, the key observation here is that when you look at the energy, actually the energy can be rewritten in terms of the average of the spins. So this is like just the sample covariance, the sample mean of the spins. And this is what we call in physics the magnetization. So here, what I'm just doing is I'm rewriting this double sum in terms of the square of a single sum. And the second term, I'm just dividing and multiplying by n. So these terms, if I define m to be the empirical mean of the spins, the energy is just a function of the empirical mean of the spins. So that's the first key observation. And so here it's very easy to identify what is the macroscopic variable that we care in the system, right? Because essentially the energy can be just written in terms of the mean. And the mean is in statistics, right? So that's going to be our summary statistics or our order parameter. So now the question, as I said, is that once you identify what is the aggregate variable that describes the behavior of the system, the question is, can I write the Boltzmann-Gibbs distribution instead of writing for the spins, can I write it for the summary statistics? So what is the distribution of the mean of the spins? So you must count how many spins there are for a given mean. So if I fix the mean, how many configurations there are for that mean, right? So I need to include this counting factor. So if you think a little bit about the problem, it's simple that this factor, the number of configurations with a given mean, is just given by this combinatorial factor, okay? And then the distribution of the system with a fixed mean is given by the energy of a given configuration, which can be described in terms of the mean, as we just saw, times this combinatorial factor. So essentially, now we have exactly the description of the system in terms of the summary statistics. And in this case, it's fairly easy, but I must also like stress that, in real life, in a real like statistical physics problem, let's say the juice of the problem is finding this description. That's where let's say, all the intuition of the physics go into. Any questions about that? Okay. And as we are physicists, we like to put this factor in the exponent. So we just put it in the exponent by taking the log. And then now we have this distribution that takes this exponential form that looks also like a Gibbs-Boltzmann distribution, but now on the summary statistics. And now the question, remember that the large deviation principle consists of understanding what is the limit of this quantity as you grow the system. So now you need to study how this quantity behaves when n is large. So notice that n appears in two places. First, as a global factor in the energy as a function of the summary statistics. And then there is, of course, an n that enters into the counting factor, which is going to be the entropy of the system. So what you can show is that if you take the log n1 over n, which is the quantity that appears in the large deviation principle, essentially, all you need to do is to look at this counting factor. The log of this counting factor, you can use Stirling's approximation when n is large, keep the first order term, and this gives rise to this potential phi, which is written here. So there is the part of phi that corresponds to the energy, which is beta over 2m squared plus beta hm. So this is just the energy part. And then there is a part that comes from the counting factor, which is the entropy part. And in this case, if you do the Stirling approximation, you see that it's just simply this, what we call the binary entropy in information theory. And so, just as I said before, when we look at the free energy, which is the energy in the space of the summary statistics, we pay two terms. There is the price of the energy of the configuration plus the price of how many configurations there are with that summary statistics, which is the entropy. And then in this space, there is a competition between these two factors. And the large deviation principle exactly is going to be the summary statistics that extremize this potential function that counts for this trade-off between entropy and energy. So in order to describe how the measure is going to behave in the limit, we need to find the configuration of m star that extremizes this potential function. And the way we find extremizers in maths is just that we take the derivative and look for for critical points, for zero gradient points. And this leads us to an equation. So if you take the derivative here, believe me, you get an equation which is like that. So you need to do some work because here you see there are some logs. So when you take the derivative of h respect to m, you're going to get like some expression. And then you need to remember that you can re-express the hyperbolic tangent as a combination of logarithms. Okay, just a trigonometric identity. And once you do that, you get a very simple equation that is m is equals to the tan h of beta m plus h. And this is what is called the saddle point equation in statistical physics. So this is the equation that describes so all extremizers must satisfy this equation. So studying the extremizers is equivalent to finding the solutions to this equation. And again, all of these might seem very standard, but this is exactly what is going to happen every time we do a computation in statistical physics in the context of machine learning. We are going to identify summary statistics. We are going to identify what is the large deviation potential. And by taking derivatives of the large deviation potential, we get a saddle point equation, and then we're going to study the saddle point equation. Here, it's just that this problem is very simple. I can do this in half an hour with you. Any questions? Okay, so let's look, now we need to study this equation. It becomes a problem about studying this equation. So let's consider the first case, which we have zero field. So H equals to 0. So we have no external field. Now notice that one thing you can already realize here is that if you look at this energy function, when H is equals to 0, there is an obvious symmetry of the system. So the system is invariant under the flip of spins, like global flip of spins. So if I send all S to minus S, because I have a product of two S's, the system is invariant. This means that any minimizer which is different from 0 is going to come with an associated minimizer, which is minus that, because the system has this symmetry. So sometimes we call this a Z2 symmetry. So H of minus M is equals to H of M. And indeed, if you take the potential and you plot it, you see that indeed you have this symmetry. Every time there is an extremizer, there is minus this extremizer, except for 0, because minus 0 is 0. So let's look at this plot. So here I'm plotting the large deviation potential. Sometimes we also call this in physics the free entropy potential, which is minus the free energy potential. So that's why we're extremizing and not minimizing. But you can choose to put a minus sign and think about minimization if you prefer. So let's look at the potential as a function of the summary statistics and as a function of the temperature, because H is equals to 0. So we just have the temperature as a parameter. So the first thing you should notice is that when beta is very low, which means that the temperature is very high, what happens? So let's try to guess first what happens, right? So since the Boltzmann-Gibbs distribution has a beta in front of the energy, when beta goes to 0, essentially becomes flat. So it becomes a uniform distribution over the hypercube. So we should expect that as beta goes to 0, essentially the mean magnetization of the system is going to be 0, because it's just like the mean of the uniform distribution of the hypercube, right? So, and indeed, that's what we observe. That's the blue curve. For beta sufficiently small, there is only one extremizer, and it is 0. Now, as soon as you start increasing the temperature, something interesting happens, is that other two extremizers, which are maxima, they appear at a certain temperature. And so, because we need to find the maximum, these now become the global maximum of the system. 0 always stays as a extremizer, but it goes from being a maximum to becoming a minimum. And here you can see the same picture in terms of the self-consistent equation. So here I'm plotting the tan H of beta M and the line M. And when they cross, you have the solutions. So essentially, there are two phases. When beta is less than a certain critical beta, M star equals to 0 is the only global maxima. And then as you start increasing beta, when beta is larger than this beta C, M equals to 0 becomes a minima, and M star different from 0 becomes a global maxima. And if you assume M star without laws of generality to be positive, you have that the two global maxima, which are degenerate because of the symmetry, are plus or minus M. And how do you find the critical temperature? So here is very easy. You essentially take the potential because essentially this is a continuous transition. You do an expansion of the potential around 0, and you find when you have this change of curvature, right? You look at the Hessian, and you see when the Hessian goes from at 0 going from being like positive to being negative. And then you essentially find what is the critical temperature. This is in these conventions of units, beta equals to 1 is the critical temperature. Okay, and that's what we call the second order or continuous phase transition. So here, yeah, so before that, let me show you one plot that also says the same thing that we just said, but now we are plotting m star as a function of beta. So essentially for beta less than beta c, which is 1, just there is only one minima, which is 0. And then when you go for beta larger than, so, which is 0, so the system essentially has all spins are like randomly, like uniformly plus or minus 1. And then when you cross above the critical temperature, the spins tends to align and to develop a global magnetization, which is different from 0. And you have two branches of this curve, one corresponding to 1 local maximum and one corresponding to minus it. Now, that's the first thing I would like to discuss. And here I would like, so far I think this is pretty classical, but now I would like just to fix a moment and think what this means in terms of algorithms, okay? So far we have been discussing the asymptotic properties of the measure, which describe the equilibrium of the system. However, as important as the properties of the minimizer are also the properties of algorithms that we're going to choose to minimize this energy. Because in machine learning, we not only want to minimize, the problem is not convex, so we're going to choose an algorithm and we're going to try to find the minimum. And how do we do this in machine learning? We usually use gradient descent. Now, gradient descent goes down, right, in the energy. So it goes down and it stops at the local minimum. So if gradient descent gets stuck, it stops. So as important as the actual global minimum for us is the point that you reach by running an algorithm. And this brings us to one aspect which is very different from equilibrium statistical physics to machine learning, is that in machine learning, we are almost never interested in equilibrium. We are always interested in out of equilibrium. So it connects to what Leticia has been discussing with you in the other course. While out of equilibrium in physics is very natural in some contexts and other contexts, equilibrium is very natural, in machine learning, equilibrium is never a natural assumption, because in the end of the day, we are never interested, whatever the minimum is of the landscape, we are interested in what you're going to reach with an algorithm. And what this transition means in terms of the algorithm. That's what I want to pause and try to motivate. So now imagine that you forget that you have spins and that you have magnetizations and you have all of this. Just think that you have this energy function and you want to minimize it. And then you want to do gradient descent. Okay, they are spins, so you cannot do gradient descent of spins. But let's say you do the equivalent of trying to minimize the energy with something like, Glauber dynamics. Glauber dynamics at a, let's say, very low temperature. What is going to happen? So in this phase, it's pretty clear, since there is only one minimum, essentially the problem is convex, the measure is log concave, you're going to go down and you're going to reach the minimum m star equals to 0. However, here is not the case. The measure is not log concave, the energy is not convex, and depending on how you initialize your algorithm, you're going to end up in one of the branches. So if you take a random initialization in the hypercube, at finite dimensions, the magnetization is going to be close to 0, but it's going to have a small component in one of the two directions, which is determined by the statistical fluctuations of initialization. And if this is positive, the algorithm is going to go into the upper branch. And if this is negative, the algorithm is going to go into the lower branch. So even though the equilibrium measure is a mixture between the two, if you minimize by gradient descent, you're going to end up in one of these two branches. And the other important fact is that if you are close to the phase transition, because this is a continuous transition, meaning that the curvature is changing continuously, close to the phase transition, 0 is actually going to be very flat. So the time that you take to escape from 0 with gradient descent is going to be very large. And this is what we call in physics critical slowing down. But now I want you to think this in terms of like machine learning. Whenever you have a learning problem where you have a second order phase transition and you initialize it on a state which is the state close to the one that becomes unstable at the transition, escaping from it is going to take you time. So there is an association between the phase transition and the time that it takes for the algorithm to converge, okay? That's the main message that I want to pass here. This connection between algorithms, phase transitions, critical slowing down. Any questions about that? This is maybe something that we don't highlight enough in the statistical physics course, because when we study this, typically we are studying in the context of equilibrium. So, okay, so now let's move to the case where we have a positive field. So without loss of generality, positive and negative is the same. You just flip the signs. So let's assume that the field is positive. And what this happens, by the way, I forgot to mention that this phenomenon where an algorithm is going to choose one of the two extremizers is what we call also spontaneous symmetry breaking in physics. Even though the energy is symmetric, the minimum breaks the symmetry. Okay, now we add a field. With the field, the energy is not anymore invariant under the Z2 symmetry, which means that now m equals to 0 is not a fixed point, and we don't have any more the symmetry. So that's what is called an explicit symmetry breaking, as a position with the spontaneous symmetry breaking. Now there are essentially two regimes. There is the regime where the field is very strong. So of course the field is biasing. The field is biasing the Boltzmann-Gibbs measure. Yeah. So if H is very strong, of course the energy is going to be dominated by the last term, which means that all spins are going to want to align with H. So we expect that, I mean, H is infinity. Essentially, the measure is also convex. There's only one minima, and the minima is the minima that align with the field, okay? So the regime which is interesting is when the field is actually positive, but not too large. Because then we really have a competition between these two terms. And so there exists a critical field, which is called the spinodal point. Below which we have like essentially two minima. So these two minima are not anymore global. There is one, sorry, these are like, I'm in the language of the free entropy, so I should say maxima. There are two maxima. And they are not symmetric anymore. There is one which is higher than the other. So there is a global one, and there is a local one. And so here, and 0, by the way, is not, even though it looks like 0 is a fixed point, is not. Like these curves are always slightly shifted with respect to 0. And so with respect to the field, there is a discontinuous point. There is a point in which when you cross this point with the field, you go from having like just one extremizer to having two extremizers. So this is exactly the metastability that we have discussed in the context of carbon. And this is what we call as well like a first order phase transition, because there is a discontinuous appearance of a new minima as a function of H. So now it's useful to have also a mental picture not only of the free entropy landscape, but it's also useful to see how this looks like in terms of the extremizer. And so here I'm showing you what is the M star as a function of H. And again, because we have these two minima, one is a global and one is a local, this is going to impact the behavior of local algorithms. So if you do gradient descent now on this landscape, essentially, if you initialize your system to be closer to the local minima, you're going to converge to the local minima and stay there, because the descent algorithm stops at the minimum. And since the energy barrier between the global and the local, it's extensive in the number of spins in the system, in the limit, you essentially stay there. So this is exactly the metastability that we saw before with beer and carbon atoms. So that's very interesting from the perspective of algorithms, because it tells you that essentially for local algorithms, metastability means that optimizing is hard, right? Means that if for some reason you get stuck into the bad minima, you will not get out of the bad minima. And you can think that, oh, let me add a bit of noise, let me add a bit of temperature, right? Let me do stochastic gradient descent instead of gradient descent. It will not help you, because the noise, it's order 1 in the space of the of the configurations. And in order for you to jump a barrier, you need something which is order n. So you need to add a noise which is extensive with the system. So you will never escape. So even for stochastic gradient descent, you will not escape this minimum. So yeah, depending on how you initialize, you're going to get in one of these two branches. And you can see that there is a discontinuous jump between the branches as a function of h. So in physics, we also talk about hysteresis and all the phenomenology connected to the physics of the ferromagnetic phase transition. But for me here, this is not the point. I just want to convey this, let's say, algorithmic point of view on this problem. So this is going to be the base of everything that we're going to do in the following. So it's very important to let it sink this point of view. We are just going to change a bit the language as we go from statistical physics to machine learning. So instead of talking in terms of particles or degrees of freedom, we are going to be talking about the parameters, right? So when you minimize the energy function, you minimize it with respect to the parameters of your neural network. So these are our spins. So these are our configurations that we are interested in. Is whatever you are minimizing with respect to. Instead of Hamiltonian, that essentially encodes the physics of the problem because the energy function, we are going to be talking about the loss function. So the loss function is a bit different from the Hamiltonian. I mean, they are the same object, you want to minimize it, right? However, the Hamiltonian is given by you, by the physics, right? Like, nature gives you the Hamiltonian and you need to deal with it. The loss function, you choose the loss function. You are the statistician. So there is some freedom to play with the loss function in order to avoid some of these problems that we have discussed for local algorithms. So there's going to be a different way of thinking about this because you have some control over the loss function. Then this is perhaps a little bit less obvious, but the connection between the interaction terms of the Hamiltonian and the data. So here in this in the Curry-Weiss model, I don't know if there is a more efficient way of doing these transitions, but the interaction between the spins is given by this first term of the Hamiltonian. And here is just, essentially the interaction is governed by the geometry of the graph that I chose to define this model, right? So here I'm minimizing over the hypercube in a fully connected graph. So this induces a certain type of interaction. I could also have considered some other graph, like the lattice, where we do study the Ising model. But I could also have considered, let's say, a Erdős-Renyi graph, like a random graph. And this would induce different interactions. So in machine learning, the role played by the interaction term that defines what are the interactions is the data. The data is what couples the degrees of freedom. So let's try to parse this for a moment. Think about training a neural network. So you choose your loss function, you have the weights of the neural network, and you want to minimize over the weights. During the training, what happens? As you run gradient descent, the weights get correlated, right? You initialize at random, and then the weights start getting correlated. And what is the correlation between the weights? Is the data, because the weights are seeing the same data at every step of the algorithm, right? So the data is the essential factor that correlates the weights during the training. So they play the role of the interaction term. Just like here, the graph is what is underlying the correlation between the spins. And finally, I already motivated, is this deep connection between algorithms and out of equilibrium physics. Again, I must say that this connection, one should have some mental flexibility about it, because while in physics the dynamics is imposed to you, right? You want to study like how to produce like a diamond, you need to heat up your carbon and you need to cool it down in a specific way such that you hit the point that you want, right? So the dynamics is the physics. It's given to you. We model the dynamics in different ways, and Leticia has been discussed different models of dynamics which are physical. In machine learning, we don't care about physical dynamics. We care about the algorithm, and the algorithm, you choose the algorithm. So you have the freedom of saying, doesn't need to be local. I can add a term, let's say like an acceleration term, I can couple with previous times of the trajectory. I can, you can play with the dynamics. So every machine learning problem that we study, we have to keep in mind that it comes with an algorithm, and this algorithm is part of the definition of the problem, but we could define a different problem with a different algorithm. It would be a perfectly well-defined problem. We don't need to satisfy questions like detailed balance or, right? We choose the algorithm, and as long as it works, it's a good algorithm. So any question about this? So this ends like the first part of today lecture, which is about this language of statistical physics. What is the goal? To compute large deviation potentials, connect these large deviation potentials landscapes with optimization algorithms, and interpret like properties like metastability in terms of difficulty for the algorithms. So for the second part of today, what I want to do before jumping into, let's say, the applications to a real problem, I would like to give you a historical context of the field, because I think that it's very important for you to keep a mental picture of the history, because if you work in this field, you will deal with people doing machine learning. They know nothing about physics, and often they can be a bit adversarial against the physicists that want to say something about machine learning. They can say, "Oh, you guys have these strange methods, and we don't understand them. We don't want to read your papers." And sometimes you can get some pushback. And what they forget is that this connection is not a new connection. And actually, I would like to claim that this connection is there as old as the field itself. And so I want to give you this history. If you don't know this history, I want to give you, so that you are not crashing into a party if you want to work in this field. You should remember the younger generation in machine learning, that physicists have been there since the 80s, and they have been working on that. So we have our space there. Yeah?
At the beginning, you talked about the relation between the free energy and the neutral information.
Yes. Maybe I can write this for a specific problem later, and I can expand. Yeah, because it's just like very simple to show mathematically in a problem. Let's say that you have a signal and you have a signal and a noise, and you want to denoise it. So the information between the noisy version of the signal and the signal itself, if you write it down, the free energy pops up. But you can also write in a more abstract way. Okay, so let's get into the science, into the history of the science. So one of the first connections between this picture that I gave to you and computer science has been established by like these three gentlemen that introduced an algorithm based on this connection. So this algorithm, you might know, is called simulated annealing. And this was in a very influential paper in '83. So let me try to read the abstract. It's not very clear, but yeah. There is a deep and useful connection between statistical mechanics, which is the behavior of systems with many degrees of freedom in thermal equilibrium at finite temperature, and multivariate or combinatorial optimization, finding the minimum of a given function depending on many parameters. So this is something we just discussed. A detailed analogy with annealing in solids provides a framework for optimization of the properties of very large and complex systems. This connection to statistical mechanics exposes new information and provides an unfamiliar perspective on traditional optimization problems and methods. So here they are really first establishing this connection between optimization and statistical physics, and going beyond it, saying this provides a way of developing new algorithms. And the algorithm that they provided here, that they introduce here, is precisely this idea that if you have your, let's say, free energy landscape, and it's a very non-convex landscape, and you want to optimize, you want to find the global minimum, maybe you should not be doing descent. Maybe you should be starting at a higher temperature. So as we go higher temperature, the measure is closer to the uniform measure. So this is convex, is a log concave measure. And so we go from a convex point to a very non-convex point as we decrease the temperature. So maybe if we find a way of decreasing the temperature in an appropriate way, we might be able to hit the good spot of the global minimum instead of just initializing and going down. So this is what is called simulated annealing. Of course, I'm not saying that it's trivial to find the good schedule. This is actually an important problem, and the answer is problem dependent, depending on the optimization problem you have in hand. But this connection between the two led these three researchers who are physicists to introduce this algorithm. And by the way, I should say that this algorithm is the most cited computer science paper before convolutional neural networks. Okay, so it's not just a thing between physicists. It had a real and major impact in computer science. And this, much before like neural networks were cool. So I would say that this one is one of the first concrete examples of this connection, and that also led to some practical applications. So the second paper that I would like to discuss with you is the paper of John Hopfield that introduced the Hopfield model. So you might know John Hopfield from the Nobel Prize, the recent Nobel Prize. So John Hopfield is a physicist. He was working in neuroscience, and he was concerned with the problem of associative memory. So associative memory is that, when we see and expose ourselves to the world, we get some information, we go to sleep, we forget part of this information. Part of this information is stored. And it's not just like that the information that we store is that you retrieve this specific information. We are also able to associate what we stored with variations of this information. So if, let's say, you learned about a new type of pastry, next time you see a pastry which is not exactly the same, but is in the same class of pastries, you're going to be able to retrieve and connect. And this is what is called the associative memory. So understanding why this happens, has puzzled neuroscientists for very long. And so John Hopfield thought, okay, there is this metastability question, right? Like there is this local minima, and these local minima are stable. So can I use these local minima as ways of storing information? So instead of seeing it as a bad thing, right, you can use it as a positive thing where you store information there, and then you find an algorithm that retrieves these specific minimas where you store them. So he introduced this model called the Hopfield model nowadays, and also he introduced an algorithm how to find it. So here I'm just going to go quick, because the idea is not to go into detail of the Hopfield model, but he introduced like a spin system with a Hamiltonian. So the interaction term is going to be parameterized by the patterns that you want to store. So these are also binary patterns. And then he introduced an algorithm that allows precisely to retrieve memories that have been stored. And then he studied, since it's a non-convex problem, you should expect that there are regimes where you can retrieve and regimes where you cannot retrieve. And then he studied exactly when this is the case. But instead of like maybe going to the maths, let me show you one example of what you can do with that. So here are very old pictures, like from probably the 80s or 90s, where you have like bike and like some people and some I don't know if it's a monkey or something, like some animals. What, sorry? Eminent mascots. Yeah, thank you, Jared. And you add noise to them, and then the goal is like to denoise it. And you use the fact that you have stored this memory and you can retrieve them in an associative way in order to remove the noise, because you can associate the noisy version with the unnoised version, and you do it following the Hopfield algorithm. So again, here I would say like one of the first connections between statistical physics, here computational neuroscience, and an algorithmic outcome out of this connection. And also this, I would claim, is the first paper that connects neural networks to statistical physics. They are not artificial neural networks, they are biological neural networks, but this first connection between neural networks and statistical physics. This paper has been very influential and has attracted the attention of many physicists to this topic. And here I want to flash a paper in '85 by Amit Gutefrand and Sompolinsky that started to ask the question, how many patterns can I store into this network before I just run out of space? I run out of, like, what is the capacity of this network? And the reason I want to flash this paper is because this is the first paper that used techniques of disordered systems in order to study neural networks. So to answer this question, essentially, they needed to compute the capacity of the model. The capacity of the model can be computed using the replica method. That is a method that was developed in the context of spin glass physics by Giorgio Parisi, Marc Mézard, and Michelangelo Virasoro, that wrote this very influential book that I guess many of you know. And they use these techniques and they establish now a technical bridge. So now it's just not a conceptual bridge between statistical physics and neural networks. We now have tools that can be imported from one side to the other. And these are the same tools that we're going to use in the future to discuss machine learning. 85. Yeah, by the way, in 2010, a mathematician trying to make sense of these tools tried to rigorously establish these results. So Michel Talagrand, and he won a prize recently, like the Abel Prize, for exactly trying to make sense of these, let's say, heuristic techniques mathematically. And you know, although for us it might not be very important, but when you work in this field and you go and you speak with people doing learning, they will say, "Oh, your methods are heuristic. Why should I believe your replica computation is true?" Well, thanks to people like Talagrand, we can build also rigorous understanding of these problems, and we can, let's say, meet the standards of these people that, let's say, are not believers of replicas, although I am a total believer of replica. Sometimes this is important. It's important to go mathematical in order to be able to convince them that what you're saying is sound, and you know, we need to speak their language. That's the point I'm trying to make. And by the way, there is a funny citation. Is it here? Yeah. In the book by Talagrand, that of course you should rush to require medical attention if this formula seems transparent to you. Okay, that's the Parisi formula, if you recognize. Okay, now I want to flash something that was going on around the same time. That this story of physicists looking at neural networks and proposing algorithms and studying is not something that was bound to the physics community. And actually, since this time, since the 80s, there was communication between physicists and people doing computer science and machine learning. So here I'm flashing one example of that. Is a school that was organized in Les Houches, which I guess some of you know, but is a school in France that is very traditional and has been the home of many very important conferences. And in 85, there was one conference called Disordered Systems in Biological Organization. And if you look at the proceedings, because all the proceedings are online, so that's very nice. You can check who were there, like the lectures that were given and what people were discussing. And if you check at the proceedings, in this school in 85, you can see people like Virasoro, you can see people like Marc Mézard, you can see people like John Hopkins, and in the same list, you can see people like Yann LeCun, who is the guy that, one of the pioneers of convolutional neural networks. And actually, if you go to the biography of Yann LeCun, he has a very nice quotation that says that, at this time, at 1985, only physicists were interested in neural networks. And my professional life truly shifted in February in a physics symposium in Les Houches in the French Alps. Like there, I met the crème de la crème of international research, which were interested in neural networks, and I gave my very first talk in English. So that was the place where Yann LeCun gave his first talk in English. And by the way, there is another anecdote that in the audience of this talk, there was his future boss that would hire him in Bell Labs, where he would move after, start working, and where he would develop the convolutional neural networks. And he was there, chatting with physicists. And it was not only Yann LeCun, so there was also Isabelle Guillon, who is a French computer scientist. And if you look at one of I think this is in a blog post that she wrote about Les Houches, she was saying, I benchmarked neural networks against kernel methods with my PhD advisors, Gérard Dreyfus and Léon Personnaz. And the same year, two physicists working close by, so I think she was in Jussieu at the time. So near Jussieu, you have where Marc Mézard and Werner Kraut were, like École Normale, I published a paper on an optimal margin algorithm called mean over, which attracted my attention. But it was not until I joined Bell Labs later that I put things together and we created the support vector machines. So again, like early interactions between computer scientists, physicists, leading to concrete algorithms that made major impact in the field. So physicists were definitely not isolated. The last paper I would like to flesh out is a paper by Gardner and Derrida, who is also a very influential paper in '87. So while the paper of Sompolinsky, Amit, and Gutenfriend, and John Hopfield, I would claim is the first paper to establish this connection, neural networks and statistical physics in the context of biological neural networks. This was the first paper that actually takes this to artificial neural networks. So you forget like the computational neuroscience aspect, and you're actually motivated by the statistical learning problem. And here they were asking the question, if I have a linear classifier, so I have a classifier that is going to separate points with labels plus or minus 1, and I want to know how many random points I can put in the space before I cannot anymore separate them. So in dimension 2 is very simple. If you put 2 points, you can always separate with a line. If you put 3 points, not anymore. So what is the answer in dimension D? So this is what is called the capacity problem. And this linear classifier is what is called the perceptron and was introduced by Rosenblatt in '58. And so this was the first time that the replica trick was used to compute a quantity that is interesting for neural networks. So here is the result. They obtain like some curves. So kappa is the margin. So you can generalize this problem and say, how many points can I classify up to a certain margin? So I allow myself to a bit of robustness. And so as you increase the margin, the capacity gets lower. And so here you see that you have a phase transition, is a second order phase transition. And you can compute using the methods that we discussed before. And this paper was highly influential and gave rise to a wave of papers that I could spend the whole day just discussing this thing. I'm just gonna show the many papers that follow the Gardner and Derrida and trying to generalize this to more complex contexts. And this establishes a bridge between, let's say, the '80s, where the pioneers of neural networks were discussing with the statistical physicists and first establishing this bridge, and this has a continuation throughout our days. So it's true that there was a period where, let's say, there was a bit of a fade out in the interest to neural networks. That's what people call in computer science the AI winter. But the activity in the physics side never stopped. So here I'm flashing just some papers by colleagues that have been working in this field, making the bridge between the '90s and nowadays. In particular, they were very much interested in what is called constraint satisfaction problems. So applications in problems like graph coloring, the traveling salesman problem, graph matching, error correcting codes, KSAT, compressive sensing, the stochastic block model. And this is just some examples. I mean, I could fill this slide with faces and references. And there is a continuation between this, let's say, connection that was started in '82 with simulated annealing and the present day. So finally, to finish this historical part of the talk, I want to say that, this point of view, I hope I convinced you that this point of view not only generated new things on the side of computer science, that there was a communication between the two sides, but also some statisticians who don't know anything about physics and were not in Lesuche and did not have direct contact with the physicists, they also started thinking that perhaps like having the mental flexibility that physics allow us could be beneficial. So here I'm showing one paper from 1995 by a statistician called Lew Bryman. So Lew Bryman was a professor in Berkeley, and he invented many machine learning methods like random forests, like bagging, boosting, are thanks to Lew Bryman. And in '95, he was reviewing papers for a machine learning conference that at the time was called NIPS, nowadays it's called NeurIPS. And he was a bit annoyed by the papers that he was reviewing. And then he wrote this position paper saying, reflections after referring papers for NIPS. And here he says, our fields would be better off with far less theorems, less emphasis on fetish stuff, and much more scientific inquiry in engineering. But the latter require real thinking. For instance, there are many important questions regarding neural networks, which are largely unanswered. And there seems to be some conflicting stories regarding the following issues. So for instance, why don't heavily parameterized neural networks overfit the data? What is the effective number of parameters in a network? So here, the question is, even though we use a very large network, maybe we can express the problem with few parameters after training. If we remove some weights, we see that things don't change. What is the effective minimal number of parameters that we need to learn a certain problem? Why don't the algorithms that we use, which are based on descent methods like gradient descent, converge to local minima? Why, even though the problem is non-convex, they are going down the landscape, why they don't get stuck in poor local minima? And when should we stop the backpropagation and use the current parameters? So that's what we call nowadays early stopping. And this is in 1995. It's like this was before like convolutional neural networks and before the growth of interest in neural networks that we have nowadays. But it's quite, I claim that we still don't understand any of the answers to these questions. It's quite visionary. And so he finishes saying that, mathematical theory is not critical to the development of machine learning, but scientific inquiry is. And then he goes on to define what inquiry is. So inquiry is sensible and intelligent efforts to understand what is going on. So for example, mathematical heuristics, simplified analogies like the Ising model. So it's not me that I'm saying, right? I mean, this was a statistician in Berkeley saying that we should think about analogies like the Ising model to try to understand these problems. Simulations, which is something that people in computer science is not, even though they write a lot of algorithms, not always we are running these algorithms. Comparison of methodologies, new tools, theorems as well, when they are useful. And here they say it's rare. And shunning panaceas. So, yeah, this is just a slide that I would like to show you because I want also to say that physics is not only a source of tools, but it's also a way of thinking of the problem. So computer science has developed a lot in a mathematical context, especially due to its connection to statistics, where theorems are important. And if you don't have a theorem to prove your result, people are not going to look very seriously at your result. However, proving theorems requires assumptions, and sometimes you need very strict assumptions to prove your theorems. And what Bryman is saying is that instead of focusing on the theorems, maybe we should look at the problem in terms of science, in terms of the scientific method. And science, theory, not theorems. And physics brings this perspective to the problem. So here I'm advocating look at the problem, as a physicist, is also bringing some not only toolbox but also mental flexibility that allows us to understand things that are hard. Like non-convex optimization is hard. People that study optimization, they do 3 courses on convex optimization, and it's very hard to go beyond that. But physicists have been doing non-convex optimization since Boltzmann, right? So having the mental flexibility also allows us to be, approach problems in a way that maybe we are not afraid if you want to establish rigorous theorems. Okay, so for the rest of the time, I'd like to discuss one particular example that has been very influential, especially over the 5, let's say 10 years in the field, which is the application of these ideas to the problem of typical case computational complexity. So are there any questions or comments about the historical part? So I hope you all now have the guns to face some angry learning theory person when you publish your papers in statistical physics of learning. Okay, so what is the problem that we are looking? It's going to be a very simple class of problems. It's called generalized linear estimation. So here we are moving out of the scope of classical physics, and we are getting towards, let's say, the realm of Bayesian inference, and consists of the following problem. I have some signal. Let's assume the signal is drawn from some distribution, P star. And then I send this signal to you. And this is sent through some channel. And this channel typically corrupts the signal, compresses the signal, adds noise. And then you observe the signal. And you want to find back, remove this, decompress, denoise, and find back your signal. So this might seem very, let's say, abstract, but this is the basis of all communication. So for example, the Zoom that we are doing here, so if there's people in the Zoom, the signal is my voice. The signal gets into the microphone, gets converted into some electrical input. This electrical input gets decomposed, gets sent to some satellite, then back to the computer of someone, is decoded, and then the person should hear my voice exactly as it is here. And if we do the job well, you're going to hear the same voice, right? Of course, sometimes it's not possible because sometimes the compression, you lose some information which is essential. But any kind of communication problem can be cast in this way. And in particular, I'm going to be considering one class of these inference problems, which is called generalized linear estimation, where the corruption process is composed by the multiplication of a matrix on the signal plus some noise. Not necessarily plus, actually. Can be any noise, can be multiplicative noise, can be any kind of noise, which is parameterized by this likelihood, which is the probability of y given x times your signal. So you multiply by a matrix, you can think this as a compression process. For example, you have a matrix that is n times d, the signal is in Rd. And so if n is less than d, it's compressing by a linear transformation, and then adding some noise through this channel. Is it the problem clear? Okay. So there is one fact that is important, and let me try to motivate this if you haven't seen it before. So the first thing is that you would like to do optimal reconstruction. So optimal reconstruction is given when you, the statistician, have knowledge about the noise process and about the distribution of the signal. This might seem too much, but I'm not giving you the sample of the signal, okay? So I'm not giving you W star. I'm just giving you the distribution of W star and the distribution of the noise. So you don't know the particular realization of the noise and the particular realization of W star. And then if you have this information, the optimal way of inverting this process is given by the mean of the posterior distribution. So the posterior distribution is the one that you use with Bayes' theorem to write what is the probability of W given the observation. You observe X and Y, and what is the probability of W given X and Y. So if you know the prior distribution, you know the likelihood, you can write by Bayes' theorem this. And the minimum mean square error, so the best reconstruction error in the square norm, is given by the mean of this posterior. So this is a theorem from statistics. It's quite easy to show. If you are interested, we can then go to the board and do it together later. But that's a fact if you haven't seen it before. This is a lower bound on the reconstruction error, meaning that any other algorithm to reconstruct can do either equal or worse than that. That's what minimum means there, is really the minimum possible error. So you can see as an information theoretical quantity, is measuring what are the fundamental limitations of removing the noise due to this compression and this noise that you added. So the goal, in order to understand what is the best possible reconstruction, is to understand this distribution. Now, this is a high-dimensional distribution, and as I motivated before, physicists have studied high-dimensional distributions. It's just that they write it as a Boltzmann-Gibbs distribution. They don't write it in this way. But, for any distribution, I can just exponentiate it with the log, and this becomes a Boltzmann distribution. And I can apply the tools that we have seen to this distribution. Okay, so you can do it. And here, there's going to be quite a big leap. But if you are interested in discussing where these formulas come from, I'm happy to do so. But motivated by the kind of discussion we had in the beginning, where I say that the key idea of statistical physics is to derive large deviation potentials for summary statistics, I claim that we can derive a large deviation potential for some summary statistics, which here I call M and M hat in analogy with the magnetization, and is a bit more complicated, right? It's not the Curry-Weiss model, but yeah, here is valid for any noise channel in any prior distribution. So of course, it's some kind of a expression that depends on these quantities. I didn't tell you what the noise process is, and I didn't tell you what the signal distribution is. Yeah. So X is a matrix that you multiply your signal. So a good way of thinking about it is think about like a compression process. So you don't observe W star plus some noise, but you observe the projection of W star into some directions, which here they are random. But imagine that you project the signal into some directions and you just observe this projection plus the noise. The noise itself is parameterized by the likelihood. So if I give you, for example, additive Gaussian noise, I could say this is like a P of Y given X times W star is equals to X W star plus some noise. But it could be multiplicative, it could be some funky, noise that comes from the engineering of the zoom, for example, and the whole process that goes into like this transmission. And of course, you can see that the formulas, they depend on the likelihood here, and they depend on the prior, which is expectation over W. And so if you give me a prior and a likelihood that you are interested, I plug here, I compute some expectations, and I have the formula. Now, the key property of this formula is that it is a formula on the summary statistic M, and M is a real number. So again, we went from the problem of studying high dimension probability distribution to study extremization over two variables, M and M hat, which is a major simplification. Because two-dimensional optimization, I can just plug in the computer and I can solve. So what is the summary statistics here? I'm not sure I wrote down, that's not good, maybe I should add, is that while in the Curry-Weiss model was the mean of the spins, here is the correlation between W star and a sample from the posterior. So if the sample of the posterior is very correlated with W star, meaning that we have a lot of information, means that N is large. Otherwise, if the posterior, like if you sample the posterior and is almost uncorrelated, then M is close to 0, and then means that probably it's hard to recover the signal. Because the minimum mean square error can be written as a constant minus this correlation. And yeah, we have a pen? Yes. Inside the box. Okay, so essentially N is equal to W star. Is another one? You cannot see this? No. Ah, sorry. Okay. So W star, transpose, W hat, and then you normalize it, where W hat is a sample from P of W given X and Y. Okay. And so the MMSE here is equal to like 2 rho, but let's say rho is 1 minus M star, where M star is a minimizer of this function. It's a complicated function. Now, how do you find this? So in the problem, doing the computation, essentially, this pops out that this correlation is the key factor that we'd like to understand, because the correlation between your estimator and the signal is essentially parameterizing the, let's say, macroscopic statistics that govern recovery. If you recover, you are very correlated. If you don't recover, you are uncorrelated. Just like the mean of the magnetization, is about knowing, whether you are in a ferromagnetic state or a paramagnetic state. Okay, so there's a formula. This formula, just for the connoisseurs in the room, is derived using the replica method. It can be proven using the tools from Talleyrand and Guerra, and it's rigorous. Now let's put this formula in the computer. Let's give a particular problem that you are interested. So I'm taking the distribution of the signal to be Gaussian. So just like very unstructured signal, there is nothing special about the signal. It's isotropic Gaussian. And the likelihood actually is noiseless. So I'm not adding any noise, but I'm taking a nonlinear function of the projection. So this is what is called the phase retrieval problem, because we are projecting and we are removing, if this was a complex signal, the phase, in the real case, you're just removing the sign. So you're removing the information about the sign of the projection. So you're removing some information, you're making harder the problem. And so here I'm plotting the minimum mean square error against alpha, and alpha is the number of observations over the number of dimensions. So this matrix X that I had before, essentially is that X in R n times D. So the number of observations is Y, is equals to absolute value of the star over 4 times. And you can add a square if you want, doesn't make any difference. But... So I'm plotting you the minimum mean square error, and I have two curves. So let's parse these curves. So there's a blue curve and a yellow curve. The blue and yellow curve, they are equal up to a certain point, and then they become different up to this point. So how do you should look at this? So this is the number of observations over the number of dimensions. So the larger the alpha, the more observations you have, the easier should it be to recover. And indeed, as alpha goes to infinity, the minimum mean square error goes to 0, meaning that if you have enough data, you always recover. However, some interesting stuff happens when you have some quantity of data, but not too much. And the amount of data that you need depends on the dimension, meaning that the higher the dimension, the harder the problem is as well. So alpha is the ratio between the two, is what we call the sample complexity. It's the complexity of the data per dimension, per unit of dimension. So the yellow curve, you transition first. So meaning that, you are recovering, you're having a better recovery rate with respect to the quantity of data you have, and the blue one you recover later. So the blue curve is the minimum mean square error. So sorry, the yellow curve is the minimum mean square error. So that's the best error achievable. Is the global minimum of this potential. While the blue curve is something else. So let's discuss this now. If you look at the potential has exactly the structure that we have discussed in the Curry-Weiss model. So in this first phase, where alpha is between 0 and 0.5, essentially the potential has only one global minimum, and this minimum is 0, meaning 0 correlation, so maximum mean square error, so mean square error is equals to 1. So in this phase, you just don't have enough information from the data to recover the signal, which is logical, right? If you have 0 data, you have 0 information, you should not be able to recover. You start adding data, at some point, you start correlating. And this starts at 0.5. As you cross 0.5, what happens? 0 stops being a global minimum and actually becomes a global maximum. So this is just like the second order phase transition we saw in the Curry-Weiss model, but now in terms of magnetization. And this is what is called a weak recovery transition. You go from having 0 correlation to having a little bit of correlation. So you should think about, you have a minimum at 0, and then this minimum just goes up, and here you develop like a minimum close to it. It's not very easy to see from this picture, but essentially 0 now is a maximum. Not a global maximum, but is a maximum. As you start increasing more the quantity of data, there is a point and where another minimum appears, and this other minimum is not a global minimum. So the global minimum is still given by this one. But this other global minimum appears just like in the spinodal transition we saw for the Curry-Weiss model. As you keep increasing the data, this other minimum goes down in energy, and at some point they cross. And they cross exactly at this transition here, at alpha equals to 1. So at this point, the second minimum becomes with the same energy as the first one, so it becomes also a global minimum. And as you keep increasing the quantity of data, it keeps going down, and then the global minimum is the one with larger n, meaning that more correlation is better, right? Like we have lower MSE. So this first order phase transition here, where the 2 points cross, is what is called the information theoretical phase transition, where you start to be able to fully recover the signal. And indeed, you can see that the yellow curve goes from being positive, like, to being 0. So here is where you can fully correlate with your signal. However, even though you can do that, the other minimum doesn't disappear. You still have 2 minimum in your landscape. So you have like the global one, which is m larger than which is n here, and the one which is used to be the global one now is the local minimum. However, this is the one closer to 0, right? So what is this? This is metastability. This is exactly what we discussed in the context of small magnetic fields. And what did we say? We say that metastability traps local algorithm, meaning that if you take an algorithm like gradient descent at initialization at random, you initialize at random, essentially you are going to converge to the first minimum, the one closest to 0, because since you don't have information about the signal at initialization, the n is equals to 0. So the fact that the minimum closest to 0 is local means that any local algorithm that is non-initialized is going to get trapped, meaning that the existence of this metastable state is implying hardness for local algorithms. Okay? And that's what we call a hard phase. It's a region in the sample complexity where, even though it's information theoretical possible to recover because the global minimum is at n equals to 1, the existence of a local minimum makes it harder for local algorithms. And indeed, to be able to find this minimum, you would need either to run exponential time an algorithm or do some non-local procedure. Yeah, so this is the picture of what meta instability implies in terms of being hard to recover the signal. Is there any questions about that? Because I think this is the most important, that's the most important slide, I would say, of today. Okay, good. Yeah.
Because I was trying to visualize this the fact that you explained to us that the M is the projection of the signal with what you are guessing at.
Yes.
So how is that? I mean, in that sense, what it means to that minimums?
So it means that it means that if you sample from the posterior, right? The typical correlation between the sample of the posterior and the signal is going to be given by the global mean. However, the fact that there exists another one that I can also go here. The fact that there exists another one means that sampling from the posterior is exponentially costly, right? Because you need to sample from this high dimensional distribution. If you would do it, I don't know, with Markov chain Monte Carlo or something like that, you're taking like exponential time in the worst case to be able to sample. So the existence of this other minimum is exactly like saying that there is no polynomial time procedure, like no local polynomial time procedure that allows you to sample from the posterior and to obtain an MMSE. So it's a statement about how hard the problem is for local polynomial algorithms. That's yeah, that's maybe like the one way of seeing it. What is interesting is that this minimum used to be the global minimum, right? Like, so the first minimum that appears is the one closer to zero. And then as you add more data, this other one, which corresponds to fully recovery, appears, and then it goes down in energy, then crosses, then becomes the global one, and the other one remains there. And all problems which are computationally hard, we conjecture, are gonna be fitting this picture. Now, I must say that, okay, maybe a disclaimer is that there are exceptions to that, and that's the statistical physics point of view on computational hardness. And to date, there are, you know, this is a research direction in which still physicists and computer scientists work to try to understand what does it mean to be hard in the typical sense. And there are different notions that have been defined. There are some equivalents that have been proven between them. But there is no consensus in which one is the best notion and whether they are completely equivalent or not. There are also some counterexamples. But this is one of them. So one of the notions of typical case complexity nowadays in theoretical computer science comes from physics and builds on this metastability, the presence of metastability implying computational hardness. So we organized a research school last year about that, bringing computer scientists and physicists to discuss how to define the right notion and whether they are equivalent or not. So I guess I'm just on time. I see 1 hour and a half here, but that's the last thing I would like to tell you today. And this is more theoretical computer science. Next time we're going to jump into machine learning. So yeah, but I'm happy, you know, to have discussions about that if in the break or after. Yeah, if you have any questions. Thank you.
So, questions?
Yep. Just jump to the takeaways.
So can you give some kind of significance to the spinodal of the full recovery minimum? Can you give some, is there any significance to the spinodal of the full recovery minimum, which you don't put on this chart?
So the short answer is no. So let me maybe try to translate Jaron's question in another language, which is, there is a point in which the second minimum appears, but it's not a global minimum, right? It's higher in energy. So is there any minimum, like deep like statement to be made about this minimum? That I know, no. This minimum only becomes interesting when it becomes when it crosses and becomes the.
I mean, if you somehow were able to initialize nearby the signal, it'd be like the Hopfield stability limit.
Indeed, yeah. If you had an informed initialization, you could sample from it. You would have higher correlation, but it would not be the MMSE. Yeah, would be not be describing the MMSE.
Thank you.
Another question? Yep.
See, I wanted to correct something in this case. Is it continue when the two minimums appear?
So no,
because I see in the incorrectly, because there was
there's a jump.
No,
I think you perfectly understood. Like, so exactly when there is this type of jump in terms of the summary statistics or minimum mean square error, means that it's a first order transition, so it's discontinuous. Because so it's something that I didn't say, but essentially you can prove that M is the derivative of the free energy. So you have a discontinuity on the derivative of the free energy. So it is a first order phase transition. However, notice that here there are two phase transitions. There is one which is second order, which is the weak recovery one. And then there is a first order exactly where you're pointing.
Another question? Other questions? So if not, let's thank the speaker again. Let's go to the coffee break.
Yes. For cautious reasons. When I arrived in Brazil, we tried our numbers on the first day before we had CPF, and the him reassured us that we could do this. It was a lie. They gave us numbers with fake CPF. Like, these numbers with fake CPF. We went to their team, and they said, oh, okay, we do this with foreigners, but here at our team, we have a CPF behind the counter we use for foreigners. So you can only change your plan if you have a picture of the CPF card. So we go back to the original tin, and they're like, why would you accuse them of this? We've never done something like this. And so in the end, the plan I had to was horrible.
And I wanted to change, and so the only way to change to me.
Thank you.
Now I have a phone number with my CPF, but it's no longer the original one I got.
So it's exactly like the connection.
Yeah.
You can use it exactly how you do, but you show it. You're gonna see is the and so the information. One term plus the other term, so you get the.
una artículo, una reflexión que dice que tipo la tecnología. Ouais, alors en fait, est-ce qu'on a de l'emploi ou de l'emploi parce que ça peut être peut-être. Ah, je sais pas. Mais No estaba muy inundada esta parte por acá, por la universidad. Y además, mira, hoy sí, ahí están las dos. Sí, me parece como 50, ya,
Corta su micrófono. Sobre. Okay, so hello everyone. I'm supposed to start soon because it seems that we have to end earlier today. So I'll try to go a little bit faster than what I thought. So let me summarize what I did until now. So in the first and second lectures, basically I justified a generalized Langevin equations beyond Brownian motion with generic memory kernels and noise-noise correlations, and these two are related by this detail balance that Fred mentioned, and that I'm also going to call today fluctuation dissipation theorem. But this relation applies to what happens to the bath. The assumption that we made when we derived these equations, that the bath was in equilibrium and remains in equilibrium, even though it's coupled to the system. That doesn't change its characteristics. So I also sketched the classical generating functional construction. I didn't discuss the time reversal symmetry, and I won't have time to do it. So if you're interested, you can have a look at the notes. these handwritten notes that I will give, and I will flash also made available in my webpage. And I didn't show the construction of the quantum generating functional, but it's very similar to the classical one. But I can also give you references for that. And okay, so important. One point to be stressed, which is important, is that if we use baths in equilibrium, and if we haven't made any mistake in the construction of the Langevin equations or focal Planck's on also generating functionals, those evolutions, we want them to be able to take the system to its own equilibrium. So the probability distribution of the configurations of the system, we want our dynamics, because we want to discuss physical systems, we wanted to approach this Gibbs-Boltzmann distribution function at sufficiently long times. So Bruno was discussing today a different perspective, so the one where you're interested in solving problems in computer science and so on and so forth. And he was insisting upon the fact that his dynamics doesn't need to satisfy physical constraints and doesn't need to necessarily bring you to this kind of distribution function, because he's not talking about physical problems, right? There will be many similarities in what we do at the physical side of things and what he's doing in computer science, and he already stressed as well. But I will focus today just on cases where there is an equilibrium measure to be reached at sufficiently long times, although the times needed to reach this measure could be very long and not accessible experimentally. So how to prove that this is an asymptotic measure? I discussed yesterday already. That can be difficult or not. You can do it at the level of Fokker-Planck or even at the level of the generating functional. And for Lindblad, there's these question marks that I was discussing yesterday. And as already said, the equilibration times can be very, very long. And what I'm going to do today is I'm going to tell you about simple problems where one can identify this equilibration time and find it to be finite, and also simple problems where one can see that this equilibration time becomes infinite, so it diverges. And these we can do at the level of a single particle example. And then this will be like a help. It will be a hint. It will give us ideas of what we have to think about to understand what's going on in many body problems in interaction, also having very long time relaxation times. So my third lecture, as I said, I will start by discussing some simple problems of single particles in evolution, and I will insist upon the fact that at the level of the evolution of the particle itself, which is now the system, there is as well a separation of timescales that arises between what happens to the momentum and what happens to the positions. They behave very differently. The momenta or the velocity can reach equilibration towards the Maxwell distribution very quickly, while the positions can still be far away from equilibrium. So within the same system, we have this coexistence of degrees of freedom that behave very, very differently. And Fred has already stressed this when he claimed that for the modeling of the active particles, one can basically neglect all the inertial effects because the time relaxation for the momentum and the velocities are so short that in practice, you always go beyond with your measurement and observations. So this happens as well for many physical problems we're interested in. And this is also what justifies the use of the overdamped description that I was already introducing in my previous lectures. So drop inertia, focus on X, separation of timescales, it's in the own behavior of the system. And it's not so surprising because, okay, we have already discussed it a little bit, both Fred and myself in my previous lectures. Now, let's have a look at a very simple problem already in the overdamped limit, when I suppose that velocities and momenta have converged to their Maxwell distribution. And look at this equation. So I have the part which has a friction here on the left-hand side. I've moved it to the left-hand side. I suppose that my particle is confined by a harmonic well potential. So this kind of potential with a spring constant K around 0. And this, as I was telling you yesterday, it can be important because it's confining the particle and not letting it go towards infinity. And it's also important because it makes the Boltzmann distribution part that depends on the position exist. Because we can have a e to the minus beta v of x with this potential form there, normalizable, because you can integrate over all space, but the fact that this goes to infinity at infinity both sides makes the integration yield a final result. So this is the noise, white noise. I'm working with a white noise Markovian equation to simplify discussions. And this is an external field that one can apply, a little bit like what Bruno was doing in the morning when he was, changing the energy of the magnetic problem by adding a magnetic field. So here it's like adding a field that will push the particle in a given direction. So depending on the sign of H, it will push it right or left. And I focus on one dimension to make, again, my calculation simple. So what do we expect for the motion of this particle? So whatever the initial condition I give to it, say that I started here at some non-zero value of x naught, it will start moving within this harmonic well, and I expect the average, because there is a symmetric well here, and I consider h equal to 0, I will imagine that the average will go towards 0. I mean, the motion will be symmetric around 0, and the average of the position of the particle will reach a 0 value after some time. And this time, I want to evaluate it somehow. So what I can do is I can solve this linear equation on x. You see that it's linear. Both terms are linear here. This doesn't depend on x. H, I set it to 0. Oh, well, actually, I can keep it here for the moment. And I can integrate that equation explicitly. And I have a piece which depends on the initial condition. I can set it to 0 if I want to start my motion from 0, but I can also keep it different from 0 if I want to start it from somewhere else. And then I have a term which has involved an integration from the initial time to the measuring time of the sources present in the equation above. So this psi and h act like sources. They depend on time, for example, and they will appear integrated over time here, psi plus h, depending on the time, integrated over time from the initial to the final time. And there will be a Green's function, so a kernel here that appears from the integration of the part of this equation that doesn't depend on the sources, so you can read it from there, that it's an exponential function of time difference with a prefactor here that I can read as an inverse time scale, which is gamma over k. Okay, so I can rewrite this. I can identify from here time, which I'm going to call the time of x, equilibration of x, which is going to be gamma over k. So I read it from here. Read it from there. And I also can read it from the first term, because it appears both, of course, in the first term concerning the decay of the initial conditions, and the second term, which concerns the full evolution of the problem. So if I take the average of this over the noise, the first term, say that it set the initial condition to 0, or I just look at times which are longer than this relaxation time, so that this has decayed to 0. So the only thing that contributes is this last term over here. So if h is equal to 0, the average of x is 0. If h is different from 0, it can drift the particle in one direction depending on its sign. So from here, I can define and calculate something which is called the linear response to an instantaneous kick. So I want to know how this average in the position of the particle changes because of the application of the field. And I can define this linear response in this way. So I can imagine that I apply my kick at a given time t prime, and I see how the position of the particle has changed at a different time t, which has to be longer than t prime because of causality, of course. So this is the theta function that ensures causality appearing on the right-hand side here. And in practice, the definition is the variation of this average of x of t under the field with respect to the application of the field at the time t prime before t, and everything evaluated at 0 field. So this I forgot to write. At h equals 0. So I apply a little kick, and then I erase the kick and eliminate the kick. And from this mathematical definition, I know how much the system responds to the perturbation. So by taking h to 0 at the end of my calculation, I consider that the perturbation is very small, right? And I only keep the linear effect that in this problem, in any case, is already linear. So if I compute from here the variation, I only have to act on this h of t second here with this variation. This gives me a delta function between the two times. It cuts the integral, and then I get this exponential outside, and there is the 1 over gamma as a prefactor. So the linear response of the position of my particle to the application of a little field, a little kick, I give a little kick to the particle at the previous time t prime, is a very simple expression. It decays exponentially towards 0, and it decays with the same characteristic time that I was reading from the exponential here and the exponential there. So I noticed that, you know, these two quantities behave, there is a characteristic time that I can start reading from these expressions. We also note that this linear response doesn't depend on the two times separately, but it depends on the two times through the difference, both in the theta function as in the exponential over there. So I can say that the result, instead of being a function of two variables, is a function of a single variable. It's a different function when I, you know, make the change in notation from a function of two variables for the function of a single variable. I could have written, you know, r bar here, but we abuse notation and we use the same expression r both here as there, although they are different objects, right? But okay, this is what you will typically see in the literature. So from the fact that the linear response is a function of time differences only, we call this property time translational invariance. Why so? Because if I change both times, so if I do a change of time t into t plus delta, and a change of t prime into t prime plus delta, with the same delta here as there, so I change both times in the same way, of course, this delta disappears because the function depends on only the difference between the two, so it's cancelled out. So this is what is expressed by this name, time translational invariance. I translate all times by the same amount, and there is an invariance in the result. It's also called stationarity because, okay, this is another name that is given to this property, and it will appear also later in different objects that I will calculate. Notice that if I look at this quantity at the same times, t prime equals to t, I have an r of 0 here, whatever is t equals, whatever is the t and the t prime, if they are the same. So this means that equal time quantities, if there is this property of time translational invariance, don't depend on time. Cannot depend on time. This is a consequence of this time translational invariance, and I will come back to this in a sec. So I have already said that I can read from these expressions a relaxation time for the position, which is gamma over k, and that depends on the friction coefficient, but also depends on the width of the harmonic potential. So k is telling you how wide is the harmonic potential. So if k is very large, the harmonic potential is very narrow. If k goes to 0, the harmonic potential becomes flat. So you see that if k goes to 0, here, the equilibration time for the position diverges. And this shouldn't surprise you so much, because if k goes to 0, what happens is I don't have a harmonic potential any longer. I have made my potential flat. The particle can go away and can diffuse away to infinity. Nothing confines it, nothing stops it from diverging from infinity and minus infinity. So then there is no Boltzmann weight to be defined, normalizable Boltzmann weight that one could define in that situation, and equilibrium statistical physics breaks down in a very simple way, just because I don't have a potential confined in my particle. Something else I want to stress here is that notice that this equilibration time for the position is very different from the one for the velocities that we have already discussed in previous lectures, which is m over gamma. It was the mass of the particle over gamma, the friction coefficient. So for a large friction coefficient, this one is very tiny, and this is why we are not considering here the velocities, and we're working in the overdamped limit. But for gamma large, okay, this one is very large. Okay, it has to be compared to k. there are three parameters playing a role here, which is the mass of the particle, the gamma, and the k. So this one could be very small, this one could be very large, especially if gamma is large and k is small. So I have this separation of timescales within this sort of trivial problem of a particle in one dimension moving in a harmonic potential. Okay, now, something else that I can say is that this linear response as a function of time difference decays exponentially, and it decays exponentially with an equilibration time, which is this one over there, and that I can see like the typical characteristic time for relaxation of the exponential growing while k decays, as I have already said. So moving towards the right in these pictures when k is decreasing. Okay. For decreasing is below, actually. For decreasing k, the equilibration time for the position increases and eventually will, diverge for k going to 0. And in all cases, in all those plots here, in all those curves here, the linear response approaches 0 at sufficiently long time differences. Can take longer or shorter, depending on the equilibration time, but they all go to 0. Another object which is better behaved when one wants to do numerical evaluations or experimental evaluations of these problems is what we call the integrated linear response, or the susceptibility, sometimes we call it. So what we do here is, instead of considering the linear response of the problem to a kick, instantaneous kick given to the particle, what we do is we look at how the system responds to a perturbation which has been applied along an interval of time that goes, for example, from t prime to t, to the measuring time. So it's like keeping the perturbation on over all these interval of times. And what this corresponds to is to integrating the response of the little kicks over the whole interval of time. So it's an integration over the previous time where the kick is applied of the linear response, and all these linear responses are evaluated at the same measuring time, which is the final one at which I measure, and is the final one that I write here in the left-hand side. So this is the definition. And if I introduce my expression for the linear response here, and I just make the integral, I notice that this is also a stationary function. It's just a function of time differences only. I'm considering t being larger than t prime, of course. And then I also see that the same characteristic time appears here. And I see that this, for very long time differences, it approaches a constant, which is 1 over the width of the harmonic well. So if I want to plot, make a sketch of how these integrated linear responses behave as a function of time difference, they're increasing functions from 0, because at equal times I haven't done anything and the integral is 0, towards this asymptotic value. And again, I see the characteristic time as being, typical time to reach some level, and then all these curves approaching this 1 over k. So this integrated linear response, as I say, is something which is more manageable when you want to do numerical evaluations in more complex systems than this one, and also experiments and so on. Now, there's another typical observable that we like to look at, which is correlation functions. So Fred has already talked about correlation functions. I talked about correlation functions when I was talking about the Langevin equation and the noise correlation functions. Now I focus on properties of the system, so I want to correlate the position of the particle at different times and evaluate it without the perturbation, without external field. A little calculation, just by correlating these expressions here, one evaluated at time t, the other one evaluated at t prime, we'll see that correlations between the noises will appear because there will be two noises. You just use the delta correlation for the noises, you integrate, do a little calculation, you will end up with this expression here, either because you chose the initial condition to be 0 and it doesn't appear any contribution from the initial condition, or because I have considered already in that initial contribution term, which I'm not writing, the limit of long times beyond the equilibration time. So what I see is that if I drop this term, which is a term that doesn't depend on time difference, but depends on the sum over the two times. So if I look at times, both of them, or one of them, the shorter one of them, which is longer than the typical time scale, again, I can drop this term, and I'm just left with that one, which is what I wrote here. And you see that I see again a stationarity arising in the behavior of the correlation function. The correlation function is symmetric with respect to the two times. You can see it from there. So this is why there is an absolute value here that makes the exponential be symmetric with respect to exchanges of these two times. And the prefactor, which depends on temperature, comes from the correlation of the noise that will appear in the calculation. And this is why this is proportional to T, temperature of the bath, and inverse proportional to the width of the harmonic well as well. So I see already stationarity in this correlation function. And this is not a special feature of these two quantities that I'm looking at. If I were to compute any kind of correlation function between any function of x and t and any other function of x and t prime and correlate them, I will see that after times which are longer than the typical time scale, and I should erase this 0 because I changed notations, that are longer than the typical time scale, I will also reach situations in which I will get a function that depends on time difference only. So this is a property, stationarity, of equilibrium evolution. If you are in a situation such that you have gone beyond the equilibration time of your variables, degrees of freedom that you're evaluating, that you're examining, then any correlation function of those should behave stationary, should be functions of time differences only. This can be proven in general, but okay, it's a little bit more difficult to prove it in general, so I'm just proving it through this simple example that also helps me later tell you other things about generic cases working on the example. So stationarity is general of equilibrium dynamics and is general of when you go look at problems beyond the equilibration timescale. Now, imagine that you want to take a t-time derivative of this expression just because you like it. Let's say I want to do that. If I do that, I observe that the dependence on the width of the harmonic well disappears. It cancels out, and I get this expression here. And now I'm considering t larger than t prime, just not to keep my absolute value and make things simpler. Okay, now let's compare. Let's compare the expression that I had before for the linear response and the expression that I have now for this derivative. If I just compare them, I notice that they are identical apart from this prefactor, 1 over kBT. So the temperature appears in the derivative of the correlation, but it was not present in the linear response. This relation is called the fluctuation dissipation theorem, and it's telling you it's another generic property of dynamics in equilibrium in a Boltzmann distribution. It got me proving in general. I had proven it through the symmetries of the generating functional in my notes, which I'm not describing because I don't have time. But if you have an interest in knowing how you prove it in general, you can look at a part of the notes, which are already in the slides. So here I see it as emerging from the solution, explicit solution of my problem moving in the harmonic well, but it's general. But there is something important which I haven't told you, which is the fact that, here, when I do this operation of taking the derivative and, getting the case disappear, this holds if k is different from 0. If k is equal to 0, in particular, I cannot drop this term here because it's 1, and also this one is 1 for k identical to 0. What I have to do is I have to do a Taylor expansion here, and if I do a Taylor expansion here, the first term goes, the second term is linear in k and cancels with this k there and gives me a non-trivial contribution. And what it will give me is diffusion. It will give me a linear dependence on time for this correlation function, which is completely different from this exponential decay that I have here. So this fact that I have stationarity and that I have FDT hold if k is different from 0. If I go to the limit of opening up my harmonic well, then I'm beyond, I cannot use ideas from equilibrium, and I can see that because all these relations, stationarity and this one will fail for this very simple problem. I go from relaxation to equilibrium to diffusion. Okay, now something else that I can do is try to see how this FDT looks like if instead of working with my linear response to an infinitesimal instantaneous kick, which I told you is difficult to measure in simulations and experiments, I go to look at how chi, the integrated linear response, relates to the correlation function. And this is much more manageable in evaluations, and this is very manageable as well in evaluations. So just by doing the integration and comparing, what one observes is that if linear response is related to correlation in this way, I do the integration and I get a constant if stationarity holds for the correlation at equal times minus the correlation itself at different times, multiplied by 1 over kBt, which comes from here. So I have a linear response between the integrated linear response and the correlation functions, both measured at the same pair of times. And I could have written this relation by using differences between times because, okay, for the stationary case, I could know that both depend on differences between times, but okay, here I kept my generic notation. So if I make what we call a parametric construction of chi against C by moving the time difference, so here I see this is a function of time difference, this is a function of time difference, and the first one is a constant. So imagine that I start from setting time difference to 0. I'm here. Setting time difference from 0, I'm here. The correlation is equal to whatever its value at equal times, which in this problem is kBt over k. And the integrated linear response is 0. So I'm starting from this point, which is at the 0 level of the y-axis, and it's this value of the x-axis. The relation between chi and c is linear through this prefactor here. So if I start moving with t minus t prime increasing, let me erase the other one, which may be confusing. So if I start moving in this direction, what I will see, this is the t prime, is that I start moving along this straight line. I start moving along this straight line with this slope minus 1 over kBt that multiplies here, and you see the minus there. And when I go to the limit in which t prime is t minus t prime is the largest possible one, I will go to correlation going to 0, because the correlation decays to 0 as well, and chi going to its limiting value 1 over k. So this FDT in this parametric construction is just a straight line with this slope of minus 1 over kBt that is completely given by the temperature of the bath, which means my system is in equilibrium. So I insist, this is what you will get when you let your times go long enough so that you went beyond the equilibration time for x, and then t minus t prime remains arbitrary. So you can t prime set it beyond the equilibration time and let t grow. And this is what you will get there. So instead of writing, if I write it in terms of time differences, this would be c of t minus t prime going to infinity. This is tt, and this is the same, chi of t minus t prime going to infinity. Okay, good. Now, this I found through this example, but as I said, again, this relation is completely general in equilibrium, so this linear relation between chi and c is also completely general in equilibrium. What can change is the value of the correlation function at equal times, the value of the linear response at infinitely separated times, but the fact that you will have a linear line like that should apply. What could happen is that the correlation doesn't decay to 0. It could happen that it decays to a finite value. For example, in the Curie-Weiss example of Bruno's today, if you are in one of the, you have undergone your spontaneous symmetry breaking, so you have to magnetize your system with a certain finite value different from 0. So this correlation will not be 0 at the end. It will be m squared, actually. This will be maybe another value, not 1 over k, whatever it is corresponding to that. But, it will be given by this linear relation as well, the chi against c construction. So something that you can do as an exercise is pick the example of my harmonic well and see what happens when you take k to 0 before taking any long time limit. So you take the problem of no potential flat space, no confining potential. So you actually are studying then a random walk, the Langevin process I was discussing with you in the first lecture. Only that for the moment in the first lecture, I was focusing on the velocity. I didn't tell you anything about the positions. But if you look at the positions, you will see that the positions diffuse, as also Fred was discussing yesterday, and the correlation between equal times positions don't reach a finite value. They grow in time with the diffusion coefficient, and this is telling you that this system is not in equilibrium because this is not stationary, it's not a constant. So diffusion is not in equilibrium. So Langevin's problem, if he didn't have walls in the Brownian problem, if he had an infinite size system where the Brownian particle could move, would be yielding this result for the position of the particle and will be out of equilibrium. Okay. So what I want to stress is that this out of equilibrium character of the diffusion process is due to the flat direction in space. So the fact that you don't have a potential, flat directions. So flat directions in the potential energy make equilibration times diverge. And in this simple problem, this is obvious how it came about, but you will see, what happens in more complicated situations of many body systems in interaction in a second. And this makes contact with Jaron's lectures. So now let me look at that very simple problem, which is a little complication with respect to what I have done. What happens if I couple the same particles in the same harmonic well to two different baths? So let's choose a bath which is like the white one, so delta correlated. The gamma that I introduced in the first lecture is just a delta times gamma f, and this is friction coefficient, and it has associated a TF. So I should have written the TF here in the right next to this. So there is a TF associated to that. And then this I will call the fast bath. It doesn't have correlation, so its velocity, its dynamics is extremely fast. But then imagine that I have another bath, which is slow, which has a different friction coefficient, and its noise-noise correlations are exponential decaying in time. Like what Fred was discussing, and I was also discussing in the context of Ornstein-Uhlenbeck particles, for example. But they're both equilibrium baths. So they both satisfy the relation between the correlations of the noise and the friction, the correlations of its noise and the friction, but they have different dynamics themselves, and they have different temperatures. One is, say, lower than the other. Let me choose this ordering of temperature. So say that the fast one is lower temperature than the slow one. So what we did before is that we had an equilibration time, a single one, that was depending on the single friction coefficient and the spring constant of the harmonic well. But now, we don't have a single friction coefficient. So is there an equilibration time for this new problem or not? And how does it depend on these two gammas and eventually the temperature? I don't know, how does my problem changes now that I have this complex bath made of two pieces? The problem is also it's simple to solve. So you can solve it in the same way because it's still linear. I only have a kernel of memory here in the friction part, and I have noise correlations in the eta, which is the one associated to the slow part, and say that the psi is associated to the fast. It's still a linear first order differential equation solvable analytically. So one can, I spare you the calculations, but you can solve this, and one can choose all these parameters, gamma fast, gamma slow, temperature, K. There's a bit of a choice of parameters to be done in such a way that one induces in the system a separation of timescales. But now it is a separation of timescales on the same variable. What do I mean by this? I just focus on the position of my particle. Position within the well, right? So what I will see, if I calculate the self-correlation of the position at different times, just like before, I will see that it decays from a value it has at equal times to a plateau, and then there is a second relaxation towards zero. It's no longer an exponential relaxation like the one I had with the single bath problem. You remember there was something like this? Just an exponential relaxation. Now I'm inducing a separation of timescales, which I see much better if I use log-log representation of my plots. And in this log-log representation of the blue curve, I see a fast decay towards a plateau, and then, a slower decay towards zero. And by tuning my parameters, the K, the gammas, and so on and so forth, I can make this plateau quite long. I can make it, rather flat and then very long, and make my second relaxation take longer. So there is a second time scale here, which appears, which depends on all the parameters, and I'm not writing it down, that characterizes how much I have to wait for the correlation to decay significantly below this value of the plateau, and I'm calling this value of the plateau Q. This is a standard notation in the field, because, okay, it will appear as a correlation of something else a little bit later in my lecture. So this is what happens for the correlation function. If I look at the integrated linear response, I see the same, but reverse. I see the fast increase towards a plateau, and then a slow increase towards its asymptotic value at the infinite long time separations. So I have this two-step relaxation induced by this coupling to the two baths that I have engineered. I have chosen the bath so that this happens. If I make my parametric construction of the chi against C, just as I did before, what I will see is that I have a linear piece with a slope, which is given by the inverse of the fast, the temperature of the fast part of the bath. So it's characterizing what's going on with the relaxation of the correlation from its equal time value to Q. So you see here is when the correlation is moving from equal time value to Q. I have this linear piece with the inverse, with the slope given by the inverse temperature and the temperature of the bath there. And then I have a second piece where I go from this Q to the maximum separation of the correlation, say 0, where I have another slope, and this is controlled by the temperature of the slow bath. So I can tune my parameters so that this separation of timescales here is very sharp, and this separation of this curve in a piecewise curve with two straight lines, I can make it also very, very sharp. So you see, from here, I realize that although stationarity is satisfied by the correlation, and I could have imagined from that measurement that this problem was evolving in thermal equilibrium, from here I noticed that it's not, because it's characterized by two temperatures. In equilibrium, I should have obtained a single straight line with a single temperature. But of course, I'm coupling my system to two baths with different temperatures. So there is no single temperature in my environment. And the environment is complex in the sense that it has two different time scales. So the system is feeling one bath here and is feeling the other bath over there, basically. This is what's going on. And all the dynamics in this fast relaxation towards the plateau of the correlation, or the relation between responses and correlations, is dictated by the fast bath. And everything which is going below that fast time scale is sort of forgetting what the fast bath has to say, and is controlled by the slow bath. So in cases in which I don't play so well with the separation of timescales, and I can have a little bit of a mixture of both, so the temperature that I can be measuring here could be a non-trivial function. It could be something which depends on parameters, not as extreme as what I was telling you before, but I can, cook up my model in such a way that I still have this separation of slopes made sufficiently sharp, and everything which is fast is the fast bath, and the other one is a mixture of effects of both. But still with a single temperature that I can read from this FDT construction, we call it, or FDT relation, or FDT parametric plot. So I can make this a little bit more general, in the sense that I can say that, imagine that I have a system where I have my integrated linear response. I take my times to be long enough so that I'm in some, asymptotic limit. I don't know exactly how long it has to be, but, some asymptotic limit, such that the times have gone beyond this characteristic time, which I'm calling T star. The correlation is equal to, I fix it to be equal to C. So I can change T and T prime by keeping the correlation being fixed and both going beyond this T star. And if this limiting procedure applied to the linear response becomes a single function of the correlation, so you see the dependence on the times, I assume that it disappears. This means that I can make a construction like this and maybe not get just a stepwise construction like that, but I can get, something like this. I don't know, something like that, a curve, perhaps, for other problems, more complicated. Particularly with playing with baths, what I can do is I can couple my system to a sequence of different baths, all with different time scales, organized in some hierarchical way, so that one is much slower than the other and is much slower than the other, and so on and so forth. And I can build up a situation where I can have, sort of a continuity, a continuous curve, which is not straight lines, but it's a curve. And, in each of those points, I can define an effective temperature that depends on the value of the correlation just by taking the derivative of this chi with respect to C. So the local slope here is giving me different effective temperature values at different correlation scales. We can call them correlation scales. Sharon. No. I will a little bit below. I can show you a case which is in the other direction, and the fact that I draw it this way is because I chose this ordering of temperatures. Had I chose, the other one, I could see something inverse. So there is no fundamental reason, but in the glassy problems there is an interpretation for that. So this is what I am going to come next. Yeah. Okay, so in the equilibrium case, I repeat, the TF is always the same, it's a constant, and it's just the temperature of the bath. While in the two-scale case that I show you as an example, I have a piecewise function with the temperature of the fast bath for C is larger than Q, the temperature of the slow bath, or a function for correlations below Q. And I can tune this by coupling to different baths. Now, other questions here. I may go beyond the limit that you gave me in time because I want to tell you things. So I think that lunch can wait. Yes, please.
Yeah, hi. I wanted to ask, like, when we're talking about two different baths, how are they like physically separated? This is like an interface, or how could we think of that experimentally?
Yeah, okay. This is a model, right? So I'm considering the case where my baths are completely separated and they independently interact with my system and they don't talk to each other. So it's an idealization that I make to show you how I can induce this kind of behavior in a very controlled way. All these calculations can be done exactly, and no approximation whatsoever. And I can tune my parameters to make the model do what I have just sketched on the slide. In real life is what is coming next. So in real life, what I claim, and it's a bit what also Fred was telling you when he was discussing dynamic mean field theory and the large D and so on, is that complex systems, what they do is that they're coupled to an external bath, which is a normal one, white, fast, nothing special, and it has a single temperature. But then cells, they organize in such a way, there is some self-organization that makes all the rest of the system act on any single variable that you would choose as a representative, like another bath. Another bath which is consistently generated through the interactions, through the internal interactions. And in the end, in simple models that we can write down and for which we can do all the calculations, and in other non-simple models which we cannot really study until the end analytically, we find things that resemble enormously this. So this gives an interpretation of what's going on in complex systems. So this is what is coming, complex glassy systems. Some other question? Okay, so let's go to complex systems now, not just a single variable. You have many variables in interaction in some complex way with the quench random couplings or the glassy problems where you have particles interacting via Lennard-Jones potentials, the kind of things that Fred discussed in his second lecture. So we have dynamic mean field theory at hand. So what is dynamic mean field theory? It's a method that he explained to get something like an effective equation on the chosen variable that looks very much like, well, let me have, I should have gone in the other direction. Okay, let me go in the other direction. That selects a variable, something like this. So it's an equation like this, where the external bath is here and there, and it's just a white bath with a single temperature. And the internal one is not one that I put by hand, like in the example, but that it's self-generated by the interactions with the rest of the system internally. Okay, so by doing different tricks, using large D, using saddle points, using approximations and things like that, one arrives at equations that are just like the previous ones. So I could keep inertia if I want, or I could drop it, depends on taste and the kind of problem I want to discuss. But okay, I wrote it here. There is the external bath piece, which is just white and normal, and there is this internal effect, which is characterized by a term like the friction one that I write here in by integrating by parts, basically, because, okay, I like to write it this way. So instead of having the derivative of the x point here, I integrate it and I have it there in the, it's like the derivative of the gamma. I think I wrote it below. Here it is. Sigma is like the derivative of the gamma before. And eta is a noise, which is now correlated. And the full difficulty is to know which is the functional form of this d and this sigma. So it turns out that in certain mean field models of spin glasses that were introduced for spin glasses, but next they were understood to be good representations of normal glasses, this sigma and this d can be calculated exactly because they are mean field from the start. So they are microscopic mean field models like Bruno's Curie-Weiss model of today's morning, only that a little bit more complicated. And for those, one can compute the sigma and the d and obtain that they are just functions, simple functions, which I write a little bit below, of the C, the self-correlation and the linear response themselves, the same ones that I was discussing before. I forgot to write it. So one example of a problem where this can be done is the p-spin model that Jaron discussed on Monday. So I recall the definition. So we have interactions between p objects, p variables, through couplings which are random, quench, random. They don't depend on time. They are taken from a Gaussian PDF, for example, conveniently normalized. And to make calculations easier, instead of working with actual spins, easing spins, one works with spherical ones, like in Jaron's talk, where one has a global spherical constraint. This is just a convenient thing. Just don't think so much about, where is this coming from? It's just one model for which the calculations can be done exactly. The equation I wrote before can be derived exactly in the limit of n going to infinity, and that the d and the sigma can be identified. And they are, as I said, functions of C and R, the linear responses of the system itself, with P a parameter, and P, to make things interesting, has to be larger than 3, larger or equal than 3, larger than 2. So this is to compare with Jaron's and also with the Fred's for the dynamic mean field theory part. Of course, now that I have this self-consistent thing where I have an equation on a single variable, but depends on the correlation of itself with itself and the linear response of itself with itself, it's much more difficult to solve. But it can be solved. So it can be solved, it can be put in a computer, and it can be solved analytically in the limit of long times. And one way to solve it is to write closed equations on the correlation and the linear response itself. So get rid of the x and rewrite everything in terms of correlation and linear response. And this is like the BBGKY that Fred was mentioning, only that is cut at the second level. So there's only two variable correlations and linear responses that appear. And similar equations can be written for the quantum problems. Cinque Dyson equations, they are called in the literature, and they are, okay. Well, it is possible to write them, and it is possible to analyze them numerically and analytically. So let me tell you a little bit about the phenomenology of these equations without showing you how one solves it, because it takes long, as Jaron knows. So these equations have a dynamic phase transition. What this means is that they behave differently if the temperature of the bath is above a critical temperature Td, or is below, which I'm going to tell you later, this critical temperature Td, which depends on J, the coupling constant, P, and that's it. So the relaxation above this dynamical critical temperature is like in thermal equilibrium. So the system is managing to arrive at an equilibrium situation. The equilibration time is finite, even in the n going to infinity limit, for which I wrote those equations. And still, what one observes is that there is a slow relaxation when one gets close to this dynamic critical temperature from above, coming from above. So there is a stationarity, there is FDT, but the correlations show a two-step form, like the one I showed you before for the sketchy example. So the correlation decays to a plateau, and then it decays to 0 in a time translation and invariant way. But the time needed to go to 0 or to go below some fraction of this plateau value increases with temperature when you get close to this Td. So this is not the same critical slowing down that Bruno was mentioning, but it's something like that. It's a little bit more complicated. So the relaxation gets slower and slower when one gets closer to this Td. So if you're an experimentalist and you get a glass, you cool down your glass, your liquid, sorry, you get a liquid, you cool down your liquid, you cool it down to some temperature, very far away from the glass transition. The relaxation is fast, nothing special. It equilibrates very quickly. You cool it down very quickly to a temperature which is close to the glass transition, a little bit above, but close. The relaxation is super slow, and it will follow a pattern like this one. It will go to a plateau, and then it will go down. So there is this separation of time scales, but within a relaxation which is stationary, like in my example of the harmonic oscillator for the correlation. If I look at the linear response compared to the correlation function, I will observe that it occurs in equilibrium. FDT is satisfied. It's equilibrium relaxation, only that it has this two-time separation of time scales that is arising because of the sluggishness of getting close to the glass transition. So this is what happens when you enter what is called the supercooled liquid phase. It's a liquid, but it's very dense, very slow relaxation, and some special properties, and it's a field of research in itself, So understanding well what is this plateau, how you approach it, how you get out of it, how to get this tau of temperature, all these issues are tricky in real situations, and it's, as I say, a field of research itself. How does one understand this separation of timescales from a real space point of view? What are the particles doing? In the harmonic potential, I knew what my particle was doing within the harmonic well, right? So now I want to understand what happens if I have a look with a microscope at my colloids in interaction or my atoms in interaction. So how are they moving? So what one observes is that if one observes their motion over time differences, which are very short, much shorter than this relaxation time that I wrote in the previous slide, the only thing I will see is that little vibrations of the particles within what we call cages. So the surrounding particles, don't let it flow around, or let it leave this confined region, let's say, this cage, and it will, do some kind of vibrations over there, as if they were a harmonic well around it that doesn't allow it to go away. So this is what you see when the correlation decays from this value to this plateau value there, and somehow this plateau value is telling you how stiff this confinement is. So it's giving you an idea of the size of those cages. While if you let your time differences increase beyond this tau of temperature, you destroy this local structure. I mean, you let the particles move as much as to change completely the configuration. So maybe my drawing is not perfect, but what you have to understand here is that, you know, the neighbors have changed, the positions have changed, things have moved more. Very slowly, not that much, but they have moved sufficiently so that I just cannot describe what's going on as vibrations within a cage. And this is why we call this second relaxation the structural relaxation, because it's there that the structure of the system has changed, has had enough time to change. But all of this, when you look at temperatures which are above TD, occurs like in equilibrium. Equilibrium properties are satisfied, the stationarity, FDTs, and anything else. Now, what happens if you cool down your liquid below this TD, temperatures which are below this TD? And now I'm not going to compare the behavior at different temperatures. I'm going to compare the behavior at different times after my quench, after my cooling down my system. So T prime here is a reference time, which is called the waiting time. So it's how much time I have waited after what we call the quench, which is this, you know, rapid cooling down performed at reference time, what we call it 0. So if we plot now for the same temperature, the correlation functions between the system at different times, so T prime and longer time T's, one observes that the curves depend on when I start my measurement. So for a short value of T prime, I would have this, say, dark black curve here. For a longer T prime, I will get the second one. For a still longer T prime, I will get the other one. So I'm not getting stationarity. The system doesn't reach stationarity. Stationarity is broken. No stationarity. So the C and T prime is different from a C of T minus T prime because it depends on when I start my measurement, on the reference time T prime. And the fact that the relaxation is slower for longer T primes is called aging, because the systems are stiffer, it's more difficult for them to relax, it's more difficult for them to change their structure when they have waited longer at the low temperature at which I'm measuring. So this is a typical feature of glasses. Now I have left the supercooled liquid phase and I have entered the glassy phase, and glassy phase evolved out of equilibrium, glasses evolved out of equilibrium, and one representation of this out of equilibrium dynamics is this aging. Okay, I have the sketch here of the times, that the relaxation gets slower when I start measuring later. Again, how do I understand this from a real space point of view? Very similarly to what I said before. So whatever happens for time differences which are below this relaxation time scale here is just like vibrations within the cage. And vibrations within the cage occur like in equilibrium. So this is like these curves here. You see all of them are together. All of them approach in the same manner. The plateau is below the plateau that they deviate. So this part of this relaxation is stationary, it's like an equilibrium, and you will see is ruled by the temperature of the bath. It's the fast part that is just doesn't see, the system is not able to have seen that it's a glass, basically. While the structural relaxation that occurs later on, that one knows, in a sense, that it cannot follow the equilibrium path of relaxation. It's too slow. And it occurs out of equilibrium. So there is a second relaxation, but it is out of equilibrium. And this is different from what happens in the supercooled liquid phase, also because if I do the construction of the chi against C in the glassy problem, for a given temperature T of the external bath, what I will see is a separation of my parametric construction in two linear pieces. One piece, the first one, is controlled by the bath. The second piece is itself determined. It selects a T star that depends on the parameters of the problem. So for the P-spin problem, well, we have an explicit expression for this T star, depends on P, depends on J. Okay, it's some very simple, by the way, expression of P and J. So it is the same and temperature of the bath. So it also enters there. So it's a very simple expression that is selected by the dynamics of the problem itself. It's the problem that decides which is this T star. So what do we know here now? Let me summarize. We know that from this construction, the effective temperature takes two values. One of the is this 1 over Tf is minus 1 over T, the temperature of the bath, and the other one is minus T star. And in my drawing, I have drawn T star to be larger than T. Why so? Well, how can I understand this? I can understand it because I have quenched my glass from high temperature. I have started from a liquid and I have cooled it down. And what this T star is telling you is that somehow the large organization of the problem of the glass remembers that initial condition in a fuzzy way, of course. It's not that it remembers the specific configuration, but it somehow remembers that it's coming from a disordered liquid situation at a higher temperature than the one at which you are now measuring, which is T. So for those cooling procedures, we always find that T star is larger than T. And this is self-generated by the system through where it was coming from, how it evolves at the temperature of working temperature, its internal interactions, so on and so forth. Now, what would happen if I were to heat my sample? Of course, this is difficult to do in an experiment because what you would, for example, ideally would like to do is to prepare your initial condition in a crystal, heat it up, put it in the situation where the crystal is no longer stable, and put it in a situation in which it would like to be a glass, and see how the crystal is destroyed and made a glass. Well, this, of course, in experiments is complicated, but in numerical simulations, it can be done. It has been done by certain groups. It can be done in simple models as well. And in those cases, you will observe that the T star is smaller than T, sort of confirming this idea that the T star has a little bit of a memory of what the system was coming from, and a memory of these large structures didn't have enough time to rearrange into their ideal configurations. They're still very much out of equilibrium, and they keep some memory in this sort of fuzzy way of where they were coming from. Now, a couple of more comments to link to what Jaron and what Bruno for sure will say, which is, can we understand what's going on from a phase space point of view? So Bruno was talking about free energies today. Landau, Ginsburg, sort of free energies, functions of the magnetization, because he was doing Curie Weiss, and the only other parameter was the global magnetization in his case. Jaron was telling you about complicated structure of free energy landscapes. So what happens if we have a look at the free energy landscape of this P-spin model, for example, and Jaron has already talked about that, and you try to identify where is this dynamics taking place? Let's go back to the cooling problem. So I started from the liquid, I cooled down, my relaxation goes somewhere. If I want to understand in the free energy landscape, where is this relaxation going? Well, first of all, I have to identify which is the free energy landscape I have to work with and try to understand the dynamics in that free energy landscape. The case of Bruno was very simple. Double well potential, because it's only a problem with one order parameter. In these problems, one realizes that one has to work with a macroscopic number of other parameters. This can be done. Maybe Bruno will talk about it. It's what is called the TAP approach for Thouless, Anderson, and Palmer. The free energy landscape of the P-spin model has been studied in great detail. And what happens basically in this relaxation dynamics is that whatever the initial condition from high temperatures, what the relaxation is doing is that it's relaxing towards this threshold level that Jaron has already explained. So some part in this free energy landscape, which is almost flat. Remember diffusion. So some part that I'm sketching here, of course, this is a 1D sketch, but you have to think that this baseline is an n-dimensional space where there are all the parameters here, and then you have this, mountainous kind of Andes-like picture over there with, mountains, valleys, but then you have an enormous part of this Andes region, which is a high plateau. Maybe like Bogota, in a sense. So it is huge. It has a lot of directions. It has some perhaps little mountains in between, but it has like, you have to think about it as a labyrinthic region, huge in phase space, and almost flat everywhere. Turns out that the relaxation of the P-spin goes there. This is the basin of attraction, if you wish, in dynamical systems terms. And what one can do is one can compute the entropy, so compute the number of points in this space that belong to this threshold, and from that compute an entropy, like what you do, in statistical physics. But this is kind of different, right? Because it's in this free energy landscape a la Landau. In Landau, there are two. So, this entropy is very simple, it's log 2 if I focus on this quantity. Here is not 2, it's huge. And this configurational entropy that we call sigma conf or complexity is something which is macroscopic. It's proportional to n. So from that, you can define a microcanonical temperature. So you can define the variation of this configurational entropy with respect to the free energy level at which you are working. So, you sit here and you look variations around F over there at this level F over there. And then it turns out that you do this calculation and you find that this T star that it's here is the same as the T star that was here in my construction, the same expression. So this gives support to that T star as being something that has a thermodynamic meaning, right? Because I can access it from different angles. It has phenomenological properties like being higher or lower than the temperature of at which you are working, which is reasonable. It has this interpretation in terms of volume of phase space, which is reachable with the dynamics. So it has a nice feeling. And okay, there are other properties which I could tell you about, but I don't have time. Now, how does one understand the fast and slow separation of timescales from this free energy landscape perspective? So by thinking about relaxation towards the threshold. So the relaxation towards the threshold at the beginning is very fast, but then when I'm here, what is going on? And what is going on is something like, I told you, this is like a labyrinth of a region which is almost flat. So you have to think about it as, imagine that a labyrinth of channels which have many directions on which they are like harmonically confined, and some directions over which it's almost flat. I'm exaggerating here with the tilt just to make the drawing more or less readable. But what you have to think about is that the fast relaxation that you see at short time differences is just letting this representative time of the system do vibrations across this harmonic direction. And then when you have a look at what happens at very different times, you have managed to drift away from the position you had here at T prime, say, to a position that you have here at T, which is much farther away and which is like diffusion. Of course, it's not exactly normal diffusion, but it's something like diffusing along these almost flat channels. And this is the free energy landscape viewpoint or point of view of how you see these dynamics. So I think I have gone a little bit fast. I'm sorry for that, but I had this threshold time that I was imposed to me. So let me just summarize and tell you, in 2 words what I have done and give you some references. So in the first 2 lectures, I introduced stochastic processes, very basic Langevin equations, Fokker-Planck, and path integrals. And my objective there was to insist upon the possibility of having non-trivial baths with correlations and memory kernels that arise very naturally when you derive Langevin equations and when you know what is the bath, when you have a model for the bath. Then today, a little bit quickly, and also Fred yesterday, we argued for Langevin equations where there are frictions and memories which are self-generated by the system itself, for which you don't know all the details, but in certain cases, largely p-spin models, dynamic mean field theory, you can argue about their dependencies on the properties of the system itself. So then you close the loop and you have a self-consistent theory to work with. That self-consistent theory is complicated, but it can be analyzed numerically, analytically, with different limits and so on. And then today, I basically gave you an overview of some properties of the phenomenology of glassy dynamics. Some, of course, there's much more to be said, but okay, this is like a first approach, let's say, to what's going on with the out-of-equilibrium relaxation of glass. So some references I gave you already. So I have a lecture notes on the Langevin part, very, very basic, but okay, you can look at them. I have another review on the annual reviews of ConMath, which is recent, about dynamic mean field theory and how it's applied in different contexts, not technical at all. But then they have a technical one in Lesouche, 2002. So there you can see, if you're interested, all the calculations on how to deal with these equations and get solutions and so on and so forth. And there are also probably some notes in my webpage. So thank you very much. And if you have questions, I am happy to answer.
Thank you, Leticia, for this tutorial course. Now we have time for 2 questions. Questions or comments?
So has the calculation been done of doing the aging solution for a p-spin model heated from the low temperature phase so that you get the upward curvature?
For the p-spin, I don't know. I know that Nicoletta Gnan and Claudio Maggi in Rome, they have done simulations. I know that Peter Holsworth, Ludovic, and Mauro Felito have looked at the 2D XY model. And there you can, start from the completely magnetized zero temperature configuration and heat up. For the p-spin, I'm not sure. Yeah,
It should be the same.
It should be feasible, yes.
It's hard because the initial condition is 1 RSV.
You can do it. Yeah. But it can be done. Yes, sure.
Okay. One last question. Comments? Okay. Thank you very much.
I'm here. So yeah, thank you.
This is our final sessions here at the Universidad Nacional de Colombia, but we continue tomorrow at the Universidad de los Andes. Do you want to say something?
Yeah, so tomorrow and Friday, the conference continue in the Universidad de los Andes. So for the entrance at the university, you should receive today a QR code in your email. Maybe you already have received. So